Hello friends, welcome to John Lewis NEET Chemistry English channel. In this presentation, we are going to see past 30 years NEET questions solved from the chapter Haloalkanes and Haloarenes. The correct sequence of bond enthalpy of carbon halogen bond is, so they are given four options: methyl chloride, methyl fluoride, methyl bromide and methyl iodide. So the same compounds are given in all the four options. So therefore this is alkyl halide compound. Rx we can take. Here the R group is same. In all the compounds the R group is CH3. Everywhere it is CH3. But the halogen differs. The halogens varying from fluorine to iodine. Fluorine, chlorine, bromine and iodine. Therefore the bond enthalpy also will vary. So first of all we need to know what is bond enthalpy. What is bond enthalpy of CX bond? So the energy required to make this bond between carbon and halogen, or the energy required to break the bond between carbon and halogen, is known as bond enthalpy. So when the halogen changes, definitely the bond enthalpy also will change. But how that enthalpy changes when halogen changes? See, all these halogens belong to 17th group of the periodic table. As we go down the periodic table, the atomic size increases. So fluorine is the smallest, and chlorine is bigger than that, and bromine is bigger than that, and iodine is the biggest. So this is fluorine, this is chlorine, this is bromine and iodine. So as we go down, the size increases. When the size increases, what will happen? The bond length will increase. So for this is fluorine, this is smallest. Then chlorine, this will be slightly larger because chlorine size is bigger. Then bromine, still it will be bigger, therefore the bond length will be still more. And for iodine, the bond length will be still longer, because iodine is the largest size of halogens, isn't it? Okay, therefore the bond length increases. When the bond length increases, what will happen? The bond strength decreases. So therefore we can conclude the bond enthalpy is inversely proportional to size of the atom. Size of the atom. That means what? Greater the size, smaller the bond enthalpy. So here which is having a greater size? Iodine is having greater size. Therefore the bond enthalpy of CH3I will be the least. Which is the smallest? Fluorine is the smallest. Therefore what will happen? When the size is smaller, the bond enthalpy will be greater. Therefore methyl fluoride will be having more bond enthalpy, and CH3I will be having the least enthalpy. Okay, now let us see the options here. So option A is starting with CH3Cl. Therefore we can remove this. It cannot be, because it should either start with CH3I or CH3F. So it is starting with chlorine, therefore it cannot be the correct order. But if you take the option B, C and D, everything is starting with CH3F. Therefore any one of them may be correct. But what we had seen, CH3F is the strongest we had seen, because fluorine size is the smallest and bond enthalpy is inversely proportional to the size. Therefore CH3F bond enthalpy will be the greatest. Therefore which is having that greater than symbol. So if you take B, CH3F, and then the symbol is CH3, after CH3F the symbol is smaller than, therefore it cannot be. And you take option C, after CH3F the symbol is greater than, so this may be correct. And option D, again CH3F, but it is followed by smaller than, so this also cannot be correct. So we need not check the rest of the things. Only the option C should be the correct one. Therefore the correct sequence of bond enthalpy of CX bond is CH3F greater than CH3Cl greater than CH3Br greater than CH3I. Hope you understood and you like it. The reaction of C6H5 CH double bond CH3 with HBr produces. So they are given four options here. So here very clearly we can understand HBr will undergo addition reaction between the two carbons in the double bond. Okay, now if you look at this, four options are given here. In the first option, Br is bonded to the carbon which are having two hydrogen, that is primary carbon. So here the double bond is only in the secondary carbon. Therefore this option is ruled out. And you take option B, and here bromination takes place in the benzene ring. So this is also ruled out. So with HBr, it will not undergo bromination. It will undergo only addition reaction in the double bond. So for bromination to take place like this, the reagent used is bromine and FeBr3. And here the reagent is only HBr, therefore this option is ruled out. So therefore, now let's move on to option C. So here the bromine is bonded to the carbon which is bonded to the benzene ring. And in the fourth option, bromine is bonded to the carbon which is bonded to the alkyl group, methyl group. So therefore these two may be the correct one. So here let us take this compound. What is the compound given? This is C6H5. I have written it in the form of benzene and then CH double bond CH CH3. So HBr will undergo addition reaction between these two carbon according to Markovnikov's rule. So here in the double bond, both the carbons are having same number of hydrogen. Therefore, the negative part of the addendum, that is the negative part of the addendum is bromine. See, according to Markovnikov's rule, it will go to the carbon which is having least number of hydrogen. But here both the carbons are having same number of hydrogen. Therefore, we need to decide based on the stability of the carbocation it forms. Suppose the pi bond breaks here, the pi bond electrons shifted to this carbon, you will get CH positive ion benzene. This is benzyl cation. So you will get benzyl cation. Suppose the double bond breaks here, that is the two electrons in the pi bond goes to this carbon and then this group will become positive. Therefore what will you get? You will get CH3, CH positive. So between these two, which is more stable? So this benzyl carbocation is more stable than this. Why? Because here it is having resonance. So here see benzene. So here it is CH positive. So what will happen here? So this electron moves here and positive comes here. And then this electron moves here, the positive comes here. And this double bond, this double bond moves here and it becomes positive. So this benzyl carbocation is stabilized by resonance. See, there is no resonance here. Therefore, this is more stable. Therefore, bromine will be bonded to this carbon only. Therefore, option C is the correct one. So in option A and C, this is not possible because in option A, it is primary carbon, but addition reaction takes place between the secondary carbons. Therefore, this is ruled out here. And here bromination takes place, but brominating agent is bromine and FeBr3. But we are adding simply HBr, therefore, this reaction is also not possible. Option C and D are possible, but out of these two, the benzyl cation, see, you need to understand here, the benzyl cation is what? So this bond breaks here and this benzyl cation is formed. That is, the two electrons in the pi bond goes to the other side. Therefore, benzyl cation is formed. Suppose the two electron comes to this one, what will happen here? So you will get CH3, CH ion. So out of these two, this benzyl carbocation is more stable than this ethyl carbocation. Why? Because this benzyl carbocation is stabilized by resonance. Therefore, this route only will take place for the substitution reaction here. Therefore, option C is the correct one. Hope you understood. The replacement reaction of tertiary halide. No, this is tertiary halide, tertiary iodide plus MF. M can be any metal, then fluoride, metal fluoride gives again the tertiary halogen compound. Here the fluorine is replacing the iodine, or the iodine is replaced by this fluorine. Here this is replacing this. This is what is the reaction. So what is the question now? So in this reaction, the reaction will be most favorable if M happens to be. So when this reaction is most favorable, when the metal is sodium or potassium or rubidium or lithium, that is whether it is sodium fluoride, MF is sodium fluoride or potassium fluoride or rubidium fluoride or lithium fluoride. Okay, now let's see now. So this is a tertiary halogen compound. This is a tertiary halogen compound. Therefore, it undergoes SN1 reaction. So this type of things you would have learnt already. Tertiary halogen compounds will undergo SN1. Primary halogen compound will undergo SN2. And then secondary halogen compound will undergo both SN1 and SN2 depending on the condition. So what are those conditions? All those things you would have learnt. But here It's a tertiary halogen compound, therefore this will undergo SN1 types of reaction, that is unimolecular nucleophilic substitution reaction. That means what? SN1 reaction is ionic reaction. SN1 is ionic reaction. It forms carbocation. See here. So this decomposes to what? The intermediate compound is carbocation plus iodine minus. Okay, therefore more the ionic, no? The MF bond should be ionic, because this is an ionic equation. The MF should be ionic compound. Which will be more ionic? So here everything is fluoride, that's fine. But among the sodium, potassium, rubidium and lithium, which is more positive, then only the bond will be more electropositive, that will be more ionic. So all of them are first group elements. They are all alkali metals. So first is lithium, then sodium, then potassium, then rubidium. So this is the first group element in the order. So when we go down, what we know? The positive nature of the metal increases. So rubidium is the most positive metal, lithium is the least positive metal among these four. Therefore, which will be more ionic? Rubidium fluoride will be more ionic, because fluoride is the most negative element, rubidium is the most positive element among the four given here. Therefore, this bond will be more ionic. Therefore, this RBF, that is rubidium fluoride, will be most favorable in this reaction. See SN1, see the tertiary halogen compound will undergo SN1 reaction. This is an ionic reaction. So therefore it forms carbocation. And in MF, that should be more ionic. Among the four metals given here, rubidium fluoride is more ionic. How can we find out that? So they all belong to the same group of the periodic table. When we go down, the positive nature increases. Therefore, the ionic nature will be more between rubidium and fluorine. So that is why rubidium fluoride will be more favorable. Or if M happens to be rubidium, this reaction is more favorable. Therefore, the answer is C. Hope you understood, you liked it. When chlorine is passed through propene at 400 degrees Celsius, which of the following is formed? So chlorine is passed through propene at 400 degrees Celsius. So what is propene formula? CH2 double bond, CH single bond, CH3. This is what is propene when chlorine is passed at 400 degrees Celsius. Okay, we need to learn the properties of propene very carefully, only then we can answer such easy questions here. So when chlorine is passed through propene at room temperature, what will happen? Since it's an unsaturated compound, it has a double bond here, it will undergo addition reaction. One chlorine will go here, the other chlorine will go to the other carbon, and double bond becomes single bond. But here at higher temperature, at 400 degrees Celsius, the unsaturation is not affected. So instead, the sp3 hybridized carbon, so the hydrogen in the sp3 hybridized carbon will be substituted by chlorine. So these two are sp2 hybridized. Because the double bond is there, these two are sp2 hybridized. Therefore, no addition reaction will take place between the sp2 hybridized or sp hybridized carbons. So instead, the hydrogen in the sp3 hybridized carbon will be substituted by one of the chlorines here when at higher temperature like 400 degrees Celsius. Therefore, what will you get here? CH2 double bond CH. So here one of the hydrogens, out of 3 hydrogens, so we can write it as 2 and 1 hydrogen, and this chlorine, and one hydrogen will combine with this chlorine, forms HCl. The other chlorine will be bonded to this CH2. Therefore, you will get CH2 bond Cl. So this is nothing but allyl, and this is chloride, therefore allyl chloride. So this is what we get. Therefore, the option is B. But you should know when we get PVC. For PVC, it is not propene. So PV is formed when polyvinyl, that is vinyl chloride. What is vinyl chloride? CH2 double bond CHCl. So this is what is vinyl chloride when it is subjected to high temperature and pressure. High temperature and pressure, what will happen? So this will polymerize to form polyvinyl chloride. So here it is vinyl chloride, not propene. Then propyl chloride. So what is propyl chloride? CH3, CH2, CH2Cl. This is what is propyl chloride. So that means over here the double bond has become single bond. Here chlorine is added. When chlorine is added, There is no way hydrogen could be added here. Therefore, this is not possible. Then 1,2-dichloroethane. So that is possible, but at higher temperature this is not possible. So here, so when chlorine is added, but here if the temperature is at room temperature, then addition reaction will take place. One chlorine will go here, the other chlorine will go here, and the double bond becomes single bond. You will get 1,2-dichloroethane. What is that 1,2-dichloroethane? CH2Cl, double bond becomes single bond, CHCl, and then CH3. This is 1,2-dichloropropane, but here it is ethane they are given. So when propene is used, you will not get ethane. So from that we can easily understand. So from prop, how can you get eth? So therefore this is also not possible. This is also not possible. This is also not possible. Only allyl chloride. So remember, when any unsaturated compound is heated with chlorine, or when chlorine is passed through an unsaturated compound, at higher temperature it will not undergo addition reaction. So it will undergo substitution reaction at sp3 hybridized carbon. So that point you need to remember. Therefore the answer is B here, that is allyl chloride. Hope you understood. It's very clear. The major product formed in dehydrohalogenation reaction of 2-bromopentane is pent-2-ene. So this is a major product. This product formation is based on what rule? Huckel's rule, Zaitsev's rule, Hund's rule, Hoffman's rule. We have to take the compound 2-bromopentane. What is 2-bromopentane? So pentane is 1, 2, 3, 4, 5. This is pentane. Then this is 2-bromopentane. So if you want to write, you can write fully CH3, CHBr, CH2, CH2, CH3. So better to learn bond line structure very thoroughly. Only then you can answer them very quickly. So suppose you start writing like this, it will eat away your time in the examination. Okay, here what is the, it undergoes elimination reaction. They have given it very clearly. The major product formed in dehydrohalogenation. Dehydrohalogenation means what? Elimination of hydrogen halide. So that is elimination reaction, minus HX. Here it is HBr, because they are given 2-bromo. Therefore HBr is eliminated. How the elimination takes place? Alpha beta. Okay, this is alpha carbon, and this is beta, and this is also beta. So from alpha carbon, bromine will be eliminated, and from beta carbon, one hydrogen will be eliminated. So either this hydrogen will be eliminated or this hydrogen will be eliminated. That is what we have to answer correctly now. So here bromine will be eliminated from this alpha carbon. Okay, fine. Now this is the adjacent carbon, beta carbon. How many hydrogens are there? Only 2 hydrogens are there. So in the other side, in the beta carbon, how many hydrogens are there? 3 hydrogens are there. Suppose the hydrogen is eliminated from the beta carbon where the number of hydrogen is less. Suppose 1 hydrogen and 1 Br is eliminated. You will get the product as what? CH3, CH. Now you will get a double bond here. Then CH, then CH2, CH3. This is CH2, CH3. What is this? Pent-2-ene. Pent, 5 carbons. Here in the second, between second and third carbon, there is a double bond. Therefore, pent-2-ene. So this is what is given as major product. See, suppose the hydrogen is eliminated from the beta carbon, which is having less number of hydrogen, then this rule is called Zaitsev rule. Suppose bromine is eliminated along with this hydrogen on the other side, which is having 3 hydrogen, more number of hydrogens here. Now the double bond will come here. Therefore, what is the product? You will get CH2 double bond, CH, CH2, CH2, CH3. What is the name of this compound? This will be pent-1-ene. So 5 carbon pent. In the first carbon, there is a double bond. Therefore, pent-1-ene. But what they are given? The major product is pent-2-ene they are given. Pent-2-ene they are given. Therefore, Zaitsev rule is the correct one. See, suppose the hydrogen is eliminated from the carbon which is having more number of hydrogen. If the elimination taking place from that beta carbon, that rule is called Hoffman's rule. So Hoffman's rule, you will get only minor product. You will get only minor product. So which will be the major product? Always Zaitsev rule will give you the major product. More percentage, more than 50% of this product will form, and less than 50% of this minor product will form according to Hoffman's rule. Then what is Huckel's rule and what is Hund's rule? See, Hund's rule you would have learnt in electronic configuration. Electrons never pair up. in equal energy orbitals until all the equal energy orbitals are singly filled. So that is no way connected here. Therefore this option C is ruled out. Then what is Huckel's rule? Huckel's rule is to find out the aromaticity. If the number of electrons are 4n plus 2 in any cyclic compound, that compound is aromatic. So n can be any integer from 0 to any number, or maybe up to 6. So that is to find out the compound is aromatic or not. So that no way connected with this reaction. Therefore A is also ruled out. Only Zaitsev and Hofmann's rule. Make sure you understand it very clearly. That is bromine from the alpha carbon and hydrogen from beta carbon. If the hydrogen is from the carbon which is having least number of hydrogen, then that is known as Zaitsev's rule. If the hydrogen is coming from the beta carbon which is having more number of hydrogen, then that rule is called Hofmann's rule. Always according to Zaitsev rule, whatever product you get will be the major product, and according to Hofmann's rule, whatever the product we get will be the minor product. You remember these points. If any question is asked based on the same principle with any other example, you should be able to answer correctly. Hope you understood this. Elimination reaction of 2-bromopentane to form pent-2-ene is, so we write the equation 2-bromopentane. What is pentane? CH3 CH2, but here it's 2-bromo they are given, therefore we can put bromine, and CH2 CH2 CH3. This is what is 2-bromopentane. It forms what? Pent-2-ene. So CH3 CH double bond CH CH2 CH3. This is pent-2-ene. So here what change has taken place? What is the first thing they are given? Beta elimination reaction. Yes, of course it is a beta elimination reaction. So double bond is formed here between the second carbon and third carbon. So this is alpha. Bromine is bonded to this carbon. This is alpha. The neighboring carbon is beta. So from here one HBr is eliminated. Therefore it is a beta elimination reaction. Okay, then B they are given follows Zaitsev's rule. See, sometimes they give S spelling and sometimes they give Z spelling. So both are correct. So follow Zaitsev's rule. So what is Zaitsev's rule? So here bromine is bonded to this carbon. This is alpha. The neighboring carbons are called beta carbon. I already explained this in one of the previous problems. The same question is repeated in a different way here. So here this beta carbon is having only 2 hydrogens. This beta carbon is having 3 hydrogens. If the hydrogen is eliminated from the beta carbon having less number of hydrogen, that is Zaitsev's rule. If hydrogen is eliminated along with this bromine from the carbon having more number of hydrogen, that is known as Hofmann's rule. So here the product formed is pent-2-ene. Therefore the double bond is between second carbon and third carbon. Therefore only this HBr is eliminated. Therefore it follows Zaitsev's rule. So it is a beta elimination reaction. It is a Zaitsev rule. And what is the third one? Dehydrohalogenation reaction. Dehydrohalogenation, that is removal of hydrogen halide. Here it is removal of hydrogen bromide. It is nothing but what? Dehydrohalogenation reaction. Therefore this is also correct. And what is the fourth one? Dehydration reaction. What is the meaning of dehydration? Removal of water. So there is no oxygen in this compound, 2-bromopentane, where water can be eliminated, which is not possible. Therefore D is not the option. So A is correct, B is correct, and C is also correct. Only D is wrong. Therefore we have to choose the option which is not having D. So only A is not having the option D. A, B, C is correct. All these things are having D. Therefore all these things are wrong. So here if you have some mathematical mind, no, without doing the elimination reaction here and thinking, we can easily find out the correct answer. See, if you read out the options, the fourth option is dehydration reaction. So since there is no oxygen here, there is no possibility of dehydration of reaction. Therefore we can omit that option D is not the correct one. But here in the given answer, 3 options are given in everything. So A has 3 options, B has 3 options, C also has 3 options, D also has 3 options. Only one option should be left out. Already we know dehydration reaction is wrong. Therefore we can choose the option which is not having D, that is the option A, which is not having D. So that way also sometime we can find out the correct answer. Therefore the correct answer is here A. Hope you understood. The hydrolysis reaction that takes place at the slowest rate among the following is, see, all the hydrolysis reactions are substitution reactions. So the chlorine will be substituted, all of them are reacting with NaOH, therefore OH minus will be the nucleophile that will be substituting chlorine everywhere. So in all the 4 compounds, this is what will happen. But which one will take place slowly, and we should know the reason, only then we can find out. So if you take option B, so it is an aliphatic compound, open chain compound. So here OH will be replacing the Cl minus, so NaCl will form, and OH will be replacing Cl. Okay, there won't be any problem. And here also it is a primary halogen compound. See, Cl is bonded to a carbon which is having 2 hydrogen. So therefore this also no problem. And OH will be substituting this chlorine. And here also, even though there is a benzene ring, here chlorine is not actually directly bonded to the benzene ring. It is bonded to the side chain. It is almost like aliphatic compounds only. Therefore here also what will happen? NaCl will form, that OH will be replacing chlorine easily. But you take option A, here that chlorine is directly bonded to benzene ring. So what happens here? That is benzene is, I'm writing the 3 bonds so that we can understand. So double bond, single bond, double bond, single bond, double bond. And then here it is Cl, here it is CH3. See what happens here is, so chlorine is having 3 lone pair of electrons here. So the lone pair of electrons are in conjugation with the double bonds in the benzene ring. So it can come here, and this will go here, and this will go here, and this will go here. Okay, so they are in conjugation. Therefore, the stability is greater, and moreover, so due to conjugation, the single bond acquires partial double bond character. Because this pair of electron comes here, and then this pair of electron is shifted to the next place. Therefore, here a double bond is created. Therefore, this bond becomes stronger. Therefore, it cannot be substituted easily. So that is why option A is correct here. The hydrolysis reaction that takes place at the slowest rate among the following is option A. Why? Because chlorine is directly bonded to benzene ring. Here, the 3 lone pair of electrons in chlorine are in conjugation with the pi electrons in benzene, and thereby it creates a partial double bond between benzene and chlorine. Therefore, this bond becomes stronger. Therefore, hydrolysis takes place slowly. Hope you understood this. See, the compound A on treatment with, so the compound A on treatment with sodium gives B. So A on treatment with sodium gives B. Okay. Then, and with PCl5 gives C. So A on treatment with PCl5 gives compound C. And B and C together give diethyl ether. So B plus C gives diethyl ether, C2H5O, C2H5. So this is what is given in this problem. Okay, now we need to find out what is A, B and C in that order. Okay, now let us look at the option A, B, C, D. The starting compound in A is ethanol, B is also ethanol, C is ethyl chloride, and D is ethanol. Okay, now when compound, suppose let us take option C, compound A is ethyl chloride. First of all, it is treated with sodium metal. So when it is treated with sodium metal, so what happens here, when any halogen reacts with the sodium metal in the presence of ether, it will undergo what's reaction? Wood's reaction. It will undergo Wood's reaction, and you will get butane here, C4H10 you will get. Okay, but here the ether presence is not given. Therefore, option C may be ruled out here. And the option may be A, B or C. All of them are starting with ethanol. Okay, that's fine. Okay, we are treating with sodium. So what is when alcohol reacts with sodium? You should have known that reaction. When alcohol reacts with sodium, the hydrogen in OH group will be liberated, and sodium will be substituting that hydrogen, C2H5ONa. Therefore, this should be the compound B. And alcohol should be compound A, because when we rule out the option C, all the other options are starting with ethanol only. Therefore, compound A should be ethanol. The compound B is sodium ethoxide. When it reacts with sodium metal, it forms sodium ethoxide. So now you look at the second option here. That is in the option A, the first compound is ethanol, the second compound is ethane. It is not sodium ethoxide, therefore A can be ruled out. And B, first option is ethanol, the second one is ethyl chloride, but what we should have got? We should have got sodium ethoxide. So this is sodium ethoxide, this should have come here. Therefore option B is also ruled out. And you look at option C, the second compound or the B compound is what? Sodium ethoxide. Therefore this should be the correct one. We need not go further. But still no, we will try to complete this question by seeing the other one. In order to find out the correct answer, we can stop here and we can choose the answer D. Option D is the correct one. But here, when A reacts with PCl5, so what is A? C2H5OH. When it reacts with PCl5, what is that? Phosphorus pentachloride. How that reacts? So the OH breaks here between O and hydrogen, and PCl5 breaks like this: Cl, PCl3 and Cl. So this C2H5 will react to this chlorine, form C2H5Cl, and then that O reacts with PCl3, forms POCl3, and H reacts with Cl, forms HCl. Therefore the products are what? C2H5Cl, this is compound C, plus POCl3 plus HCl. Now compound B and C should react. What is compound B? Sodium ethoxide, C2H5ONa, plus what is compound C? Ethyl chloride, Cl, C2H5. So what happens here? Sodium chloride will go away and then diethyl ether will form. What is the name of this reaction? So this is Williamson synthesis. What is this? Williamson synthesis. Therefore, so in order to answer this type of questions, here we should have learned 4 concepts very clearly. What are they? First one, Wood's reaction. By that we can eliminate option C here. And the second one, when alcohol reacts with sodium, you will get sodium alkoxide plus hydrogen gas. And third one, when alcohol reacts with PCl5, we will get halogen compound. And the fourth one, what is Williamson synthesis? If we know all these 4 concepts very well, we can apply all of them here and we can derive the answer. Therefore here the correct answer is option D. Compound A is ethanol, B is sodium ethoxide, and C is ethyl chloride. Hope everything is clear. You understood it properly. The compound C7H8 undergoes the following reactions. Okay, C7H8 treated with chlorine and subjected to heat, we will get A, and then bromine and Fe, you will get compound B, and zinc and HCl. So this is bromination. A to B is bromination, and B to C, zinc and hydrogen chloride, is a reducing agent. Reducing agent. Then here the first one, C7H8. First of all, we need to find out what is C7H8. So look at the option here. They all end with toluene, 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 toluene. Therefore, compound the compound C7H8 could be toluene. But let us see here how we can derive that. So the carbon-hydrogen ratio in C7H8, the carbon-hydrogen ratio is almost 1:1, and the number of carbon is 6 or more, then it could be aromatic. Therefore, definitely it should have a benzene ring here. So the number of carbon is more than 6, and then the carbon-hydrogen ratio is 1:1. So benzene is C6H6. But there are 7 carbons, therefore one more carbon here, 1 hydrogen should be substituted. Therefore this will be C6H5, and here it is C. How many hydrogens? 8 hydrogen, therefore it could be 3 hydrogens here. Therefore this is toluene. So we can derive, we have to think and find out what is a compound C7H8, or we can find out from the suffix of the given options. No, everywhere it is given toluene, therefore the compound may be toluene. Okay, that's fine. Okay, now let us take toluene. Let us go one by one. So this is toluene. First it is treated with what? Chlorine subjected to heating. So when it is treated with the chlorine at higher temperature, what will happen? Substitution reaction will take place. It will not undergo addition reaction in the double bonds. Therefore the hydrogen in this carbon, that is sp3 hybridized carbon. Already I have told you, when chlorine is passed through at higher temperature, substitution reaction will take place at sp3 hybridized carbon. Therefore here all the 3 hydrogens will be replaced or substituted by chlorine. Therefore what you get? You get 3Cl like this. And here the 3 hydrogens will combine with 3 more chlorines here. So you can take 3 chlorines here. So minus 3HCl, that will be eliminated. Okay, what is the next one? It is treated with bromine in the presence of iron. So this is a brominating agent. This is brominating agent. So Br plus will be the electrophile, and that will be substituting one of the hydrogens in benzene ring, where whether it is in the ortho, para and meta, it will substitute in the meta position. The hydrogen here will be substituted. I will tell you why it substitutes in the meta position, why not in the ortho. So ClCl, and you get, okay, here bromine substituting that hydrogen, meta bromo trichlorotoluene. Okay, then what is the final thing? It is reduced by using zinc and hydrochloric acid. So what will happen? These 3 hydrogens, these 3 chlorines will be removed. Instead 3 hydrogens will be added here. Therefore what will you get? Again you will get toluene CH3 plus in meta position you will get bromine. So meta bromo toluene will be the compound C, meta bromo toluene. So here you need to understand how or why this bromination takes place at meta position. See, you take here, so chlorine is highly electronegative than carbon. Therefore, by pulling out this paired electron towards itself, they all become partially negative. Therefore, this carbon becomes what? Partially positive. Therefore, what will happen? So the electrons will move here. Therefore, what will happen? So this becomes plus, this becomes positive. Now since this becomes positive, this also will come here, and this point or this carbon will become partially positive. Now again this 2 electrons will be shifted here, and this place will become positive. So when these places ortho and para positions are positive in nature, therefore electrophile cannot attack the ortho and para position, and the meta positions are relatively negative in nature. That is why this bromination takes place at the meta position. Okay, that's why meta bromo trichlorotoluene is formed here. That is compound B. And when it is reduced with zinc and hydrochloric acid, so removal of chlorine and addition of hydrogen is reduction. Therefore, toluene is formed. Therefore, compound C is meta bromo toluene. Therefore, which option is correct? Here, option D is correct. Hope you understood it and everything is clear. Identify A and predict the type of reaction. So what is this compound? This is anisole, and in the meta position there is bromine. Therefore meta bromo anisole. So if you write it like this, it will be clear. This is meta bromo anisole. So when it is treated with the NaNH2, what is the product formed? So this is meta substituted anisole. Therefore, this will undergo substitution reaction in the same meta position. Therefore, this bromine will be substituted by NH2 here. Therefore, you will get CH3O, and in the meta position you will get NH2. So it undergoes substitution reaction. Therefore, what will be the correct answer here? Where it shows substitution reaction. Yes, this is a substitution reaction. And in the same meta position, bromine is substituted by NH2. Option D is correct. But if you try to understand the pathway, how this product is formed, it is slightly difficult and different from what you think. See, first of all, this bromine and hydrogen in this position will be eliminated, and you will get benzene intermediate. So you will get a triple bond here, and then OCH3. So this is benzene intermediate. This is highly unstable. This is highly unstable. So here how this is formed here is, so when it is treated with the NaNH2, NH2 is the nucleophile. So this will remove this hydrogen, and this electron will come here, and then this bromine will be eliminated. So thereby we will get, see, suppose we take this way, it will be very clear. So suppose you take the double bond here, and this is hydrogen, and this is bromine, and this is OCH3. So here this NH2 nucleophile is attacking this. So therefore what will happen? This proton will be absorbed by this NH2 minus nucleophile, and this electron comes here and makes a triple bond here, and this bromine goes out as Br minus. So this will be the intermediate here. This will be the intermediate, and this will be highly unstable. Highly unstable. This is called benzyne intermediate. Benzyne intermediate. So therefore here, this is overall it is a substitution reaction, but first elimination takes place and then addition of NH2 takes place here. First elimination of bromine takes place and then addition of NH2 takes place. Therefore it is elimination followed by addition reaction, but overall it is a substitution reaction. So therefore here the option D is correct, because option D, it is given as what? This NH2 is substituted in the same meta position. If you take option A here, so that NH2 comes in the ortho position, whereas Br was in the meta position. But meta-bromoanisole undergoes substitution only in the same meta position. That's why this option D is the correct one here. Hope you understood this and everything is clear. Consider the reaction CH3, CH2, CH2Br plus NaCN gives CH3, CH2, CH2Cn plus NaBr. So here it has undergone substitution reaction. This bromine is substituted by Cn. This is a substitution reaction. But what type of substitution it undergoes? We know there are two types of substitution reaction. Unimolecular nucleophilic substitution reaction and bimolecular nucleophilic substitution reaction. Here this will undergo SN2 types of reaction. Why? How do I know? Or how you can find out this is SN2 type? So what type of halogen compound it is? So this is a primary halogen compound. This is a primary halogen compound. So what is primary halogen compound? So here bromine is bonded to this carbon, which is having two hydrogen, then it is primary. If it is having only one hydrogen, secondary. If it is having no hydrogen, that is tertiary. See, the primary halogen compounds generally undergo SN2 types of reaction. Okay, so now the reaction will be the fastest in, so they are given some solvents here, ethanol, methanol, N-prime dimethyl formamide and water. So they are given 4 solvents. In which solvent the reaction will be the fastest, they are asking. But now we have determined this will undergo SN2 types of reaction. So SN2 types of reaction will undergo the fastest way in what type of solvent, that we should know. So here ethanol, what is the formula of ethanol? C2H5O minus and H plus. So this is a polar solvent and also protic solvent. This is having H plus ion. And second one, B is methanol. So methanol also, it is a polar, plus and minus charges are there, and also proton is there. Therefore polar protic solvent. And you take D, water, so water is HOH. So here O is delta minus and hydrogens are delta plus, because oxygen is more electronegative. This electron pairs will be pulled towards oxygen, thereby it attains in partially negative and hydrogen attains partially positive. So this is a polar solvent and also this is having proton, H plus ion. But if you take option C, that is N-prime dimethyl formamide. What is formamide? HCO NH2 is formamide. But what is dimethyl formamide? These two hydrogens are replaced by CH3 group, CH3. That is why N-prime dimethyl formamide. So here, so it is a polar solvent. So here is oxygen. Oxygen does what? It attracts the electron, thereby it becomes partially negative, and this carbon becomes partially positive. And here also there will be an electron pair. Okay, so therefore we come to know it is partial. It is a polar solvent. We understood this is a polar solvent, but there is no proton in it, no H plus ion in this solvent. Therefore this will be favoring the SN2 types of reaction. So what you need to know is polar aprotic solvent supports the SN2 reaction. So among the 4 solvents given here, ethanol, methanol, N-prime dimethyl formamide and water, only option C, that is N-prime dimethyl formamide, is a polar aprotic solvent. It is not having H plus ion in it. So therefore this only will favor the SN2 reaction. Therefore the correct answer is option C here. See what you need to do here in order to answer this type of question, whether the substitution reaction is SN2 or SN1. See, SN1 reactions are supported by polar protic solvents. See, ethanol, methanol and water are polar protic solvent. If it is SN1 type, these three solvents will favor that reaction. But here there is SN2 reaction. SN2 reactions are favored by polar aprotic solvent. Among the four solvents given here, only N-prime dimethyl formamide is polar aprotic solvent. Therefore, that is the correct answer. Hope the answer is very clear to you and you understood it very clearly. Which of the following biphenyls is optically active? Okay, first of all, we need to know what is biphenyl compounds. So there should be two benzene rings bonded to each other. So this is one benzene ring and this is another benzene ring. So they are bonded together and therefore it is called biphenyl. So these type of compounds are optically active under two conditions. So in fact they do not have any chiral carbon because every carbon is having a double bond. Therefore there is no chance of a carbon bonded to four different groups. Therefore there is no chiral carbon, yet they exhibit optical isomerism. How? So in biphenyl compounds there are two conditions to be optically active. So the first one is both the benzene rings should be substituted in the ortho position. See, they should be ortho substituted. One thing. Then second thing, whatever is substituted in the ortho position, they should be unsymmetrical. It should be unsymmetrical. Okay, now first let us see these two conditions here. See, for first benzene here, so this is the bond connecting these two benzene rings. Therefore this is the ortho position. This is also the ortho position, two ortho position. So these two should be substituted. So here A and B, let us see. And similarly for the other benzene ring, so this is a bond connecting the two benzene ring. Therefore this and this are the ortho position. So here also it should be it should have substituents. So let us say it is C and D. It is having C and D. Okay, that's fine. Now, so if you divide this compound into two along the axis which is connecting the two benzene ring. So this is called achiral axis because there is no chiral carbon, but yet it exhibits optical activity. So this axis is called achiral axis. So it is not having four different groups bonded to it, but still it is optically active. Therefore this axis is called achiral axis. So if you divide the benzene like this into two halves, that A and B should not be the same. A and B, the two substituents in the same benzene should not be the same. Similarly, the other benzene ring in the ortho position, what is substituted? C and D are the substituents there. These two should not be the same. They should not be the mirror image of each other. So that is why we have written unsymmetrical. That is very important point. Okay. Then how can it be? See, they are if they are in the same plane, it may not be optically active. See here, both the benzene rings are ortho substituted. Therefore, when the big ortho groups are there together, there will be steric hindrance. Therefore, in order to minimize that, what will happen? One benzene ring will turn vertically. See here, one benzene ring will be horizontal like this. And the other benzene ring will turn into vertical like this. So they turn vertical. So one will be along the plane and the other one will be vertical like this. They will be perpendicular to each other. So they are now they are not having plane of symmetry. So they are in different planes now. This is horizontal and this is vertical. That will be different. Why? Due to the steric hindrance in the ortho position, they twist so that the repulsion is minimum. When it will be minimum? When they are 90 degree apart. That's why one is horizontal, the other one is vertical. So now they are out of symmetry. So therefore it exhibits optical isomerism. Now with this explanation, with these conditions, let us see one by one now. You take option A, there is a substituent here, there is no substituent here, so we can omit this one. And second one, no substituents here anywhere in the ortho position, so we can leave it out. And here in both the ortho position there are substituents, but these two are same, and in the other one there is no substituent, therefore this also cannot exhibit optical isomerism. Therefore without checking anything we can say option D is the correct one. But let us check whether it obeys all these conditions here. See, in the ortho position there are substituents, okay, these two are different, fine. And similarly the second benzene ring also in ortho position there are two substituents, and when you divide this they are not mirror images, they are unsymmetrical. And therefore what will happen here? So the bromine and bromine will repel each other, iodine and iodine will repel each other. Therefore one of the benzene will appear vertical, the other one will be horizontal. So they will be 90° apart. So therefore the plane of symmetry is also not there. Therefore it will be optically active. Hope everything is very clear. So I repeat one more time. In biphenyl compounds there need not be any chiral carbon. But what are the conditions to be optically active? In both the benzene ring, ortho group should be substituted. In each benzene ring, the ortho substituent should be different. Okay, then what is the second condition? So that is what is unsymmetrical. Then there should not be any plane of symmetry. So in the ortho position, there will be repulsion. That will be automatic now. When both the benzene rings are substituted in the ortho position, due to steric hindrance, it will twist itself so that the strain is minimum. So automatically they will be out of plane. Okay, so therefore compound D is the correct answer. For the following reaction, so they have given three reactions, A, B and C. What is the question? Which of the following statement is correct? Okay, first let us read the statement, only then we can come to know, okay, what to look for in those equations or in those reactions. So A is elimination, B and C are substitution reactions. Okay, I think we need to find out the type of reaction. Okay, now let us take reaction A. So bromopropane, this is bromopropane with KOH gives, what is here? Propene. So what is eliminated? HBr is eliminated. So Br from this alpha carbon and one of the hydrogens from the beta carbon is eliminated. That's why double bond has come. Therefore this is elimination reaction. And you take reaction B. So this is 2-bromopropane plus KOH. It forms 2-hydroxypropane or propane 2-all. So here what has happened? This Br is substituted by OH. So 2-bromopropane. Here it is 2-hydroxypropane or propane 2-all. So here bromine is substituted by this OH. Therefore this is substitution reaction. Therefore reaction B is substitution. See, what about the third one? Here what is this? It is hexene, but only one double bond, am I right? So here the Br2 is added to that. So here one Br is added and another Br is added here. The double bond becomes single bond here. So therefore here what has happened? So the bromine is added here. See here. So this bromine, Br, this bond is broken. One bromine is added to one side of the double bond. The other bromine is added to the other side of the double bond, and thereby bromine is added to that compound. Therefore 1,2-dibromocyclohexane. So that is a product. We are least bothered about name of the compounds. Here what change has taken place. So here addition reaction has happened. Therefore what is the answer? Reaction A is elimination, reaction B is substitution, reaction C is addition. So let us see one by one. A is elimination, that's correct. But B and C are substitution, that's wrong. A is substitution, that is wrong. A and B are elimination. A is elimination but B is substitution, therefore that is wrong. And option D, A is elimination, correct. B is substitution, correct. And C is addition, that is also correct. Therefore option D is the correct one. Hope it's very clear. So the possible stereoisomers of CH3, CHOH, COH, this is lactic acid, which are optically active are called. So this is lactic acid. Here this carbon is chiral carbon. See, carbon should have 4 bonds, fine. And one is bonded to the first CH3 group. And the second is bonded to the hydrogen. And the third bond is bonded to OH. and the fourth bond is bonded to the remaining COOH group. So now this carbon, all the 4 bonds are bonded to different groups. Therefore, this is a chiral carbon. Therefore, it exhibits optical isomerism. Okay, here, if you take option C, they are given mesomerism. But it cannot be mesomerism because it is having only one chiral carbon. So for mesomerism or for mesomers, there should be at least 2 chiral carbons. 2 chiral carbon, but it is having only one, therefore that is ruled out. And if you take option A, heteroisomers. So what is that? There should be 2 benzene ring. There is biphenyl compounds. Heteroisomers exist only in biphenyl compounds. But here it is a lactic acid. There is not even a single benzene ring. Therefore this is wrong. Therefore option A is also wrong. So it could be either enantiomers or diastereoisomers. So here, if you take this mirror image of this one, so you'll get C, and hydrogen will be there, and here it will be OH, and here it will be CH3, and here it is COOH. See, if you take compound A and compound B, these 2 isomers, so they are mirror images of each other. They are mirror images of each other. Therefore, it could be enantiomers. If it is not a mirror image of each other, then it could be diastereomers. So both are optical isomers. Enantiomers and diastereoisomers are optical isomers. They exhibit optical activity. But in enantiomers, both the isomers should be mirror image of each other. Whereas in diastereomers, they should not be, or they are not mirror images of each other. But here they are mirror images of each other. Therefore, the answer is enantiomers. The option B is the correct one. Hope you understood this very clearly. In an SN12 reaction and a chiral center, there is inversion more than retention leading to partial racemization. 100% retention, 100% inversion, 100% racemization. So it is a chiral center. Therefore, this carbon should have 3 or 4 different groups. Let us take A, B, C and D. So let us take D is the leaving group. So in SN1 reaction, so what will form? Carbocation will form. So here this chiral carbon is sp3 hybridized. But here the intermediate thing will be in SN1 reaction. A, B, C and D is gone. So therefore it is what? It is a sp2 hybridized carbon here. Now the empty p orbital may be projecting up and projecting down. Now the incoming nucleophile can attack from both ends, therefore racemization is possible. Therefore racemization is possible. And the other thing depends on, the other isomer depends on what? The shielding effect of A, B and C. Suppose they are too small and the nucleophile can attack from the backside. And it depending on the shielding effect of the groups bonded to the chiral carbon. Therefore, there will be inversion of the structure. When this is possible, there will be inversion of structure, and therefore that is also possible there. Therefore, option A is correct here. Inversion more than retention leading to partial racemization. See, it all depends on the steric effect or the bulkiness of the A, B, C and D. But inversion will be slightly more than the racemization in chiral centers. That's very important here. So the question here is based on all chiral centers. So that we should not forget. That should be considered to answer this type of questions. Hope you understood it clearly. Which of the following compounds will undergo racemization when solution of KOH hydrolysis? So when it undergoes hydrolysis, here the primary halogen compound, this is also primary halogen compound, and this is also a primary halogen compound, whereas this is tertiary halogen compound. See, among these 4, which one will undergo SN1 type? See, only tertiary halogen compounds will undergo SN1 type. So that means what? It can form carbocation. Therefore here H, C, CH3, C2H5, and this is carbocation plus Cl minus. So when carbocation is formed, now this carbon has become sp2 hybridized. So here in tertiary carbon, this is sp3 hybridized because all bonds are single bonds. Here now one bond is gone, it has become carbocation. Now it is sp2 hybridized. That is, carbon will be in the middle, and these three groups, that is hydrogen, CH3 and C2H5 are here. Now the empty p orbital, no, this will be pointing up and also pointing downwards. Therefore, during hydrolysis, the OH nucleophile can attack from this side, from the upper side, or from the backward side, or from the downside. So it can attack from both sides. Therefore, two different products are possible. That is why it will undergo racemization. So therefore, only compound C will undergo racemization, because all the other three compounds are primary halogen compound. They all undergo SN2. They all undergo SN2 type. Only the tertiary halogen compound will undergo SN1 type. Therefore, a carbocation will form, and the nucleophile can attack from both ends. Therefore, a mixture of two different products will form. That is what is called racemization. Therefore, only option 4 can form or can undergo what? Racemization reaction. Therefore, here which option is correct? A is wrong, B is wrong, C is wrong, D is wrong, because there are two different options here. But only 4 only is given in option E. Therefore, option E is the correct answer here. Hope it is clear and you have understood it properly. So given 1 and 2 are, okay, here they are given two different structures. They are asking they are identical, pair of conformers, a pair of geometrical isomers, a pair of optical isomers. So the structures are different, therefore it cannot be identical. See, the spatial difference is there, therefore it cannot be identical. See, here CH3 is there, here there is no CH3. So therefore the spatial difference is there, therefore it cannot be identical. Then a pair of conformers, that is possible, because here it looks like one is eclipsed and the other one is staggered structure. Pair of geometrical isomers may not be possible because there is no double bond here. Therefore, geometrical isomers may not be possible. A pair of optical isomers may be possible if there are chiral carbons, but they are just by looking at the structure we can easily identify they are conformers. Very easy to identify. One should be staggered, the other one should be eclipsed. See, if you look at structure 2, and if you are just standing here, and if you are looking at, this is the first carbon, and the CH3 is in parallel line with another CH3 at the back carbon. Similarly, the hydrogen in front carbon is in parallel line with the backside carbon. Similarly, bromine also in parallel with the other one. Therefore, it is eclipsed structure. Therefore, it is eclipsed. Whereas now you look at the first one, so maybe you can stand here and see from this end. So here if you look at hydrogen and hydrogen are opposite, CH3 are opposite, and bromine are also in the opposite direction. They are not parallel. Therefore, it is called staggered structure. So one is staggered, the other one is eclipsed. Therefore, it should be a pair of conformers. Therefore, option B is correct. Hope it's very clear and you understood it properly. Which of the following does not exhibit optical isomerism? Malic acid, alpha amino acids, lactic acid and tartaric acid. So here optical isomerism is exhibited by a compound having chiral carbon. That means what? The carbon should be bonded to 4 different groups, maybe A, B, D and E. See, all the 4 groups bonded to the carbon are different. Then this carbon is called a chiral carbon. So anything not having this chiral carbon cannot exhibit. Here what they are asking, which of the following does not exhibit, that we have to be careful. Therefore we have to write the structure of all these compounds and then we have to check whether it has chiral carbon or not. If there is a chiral carbon, that will exhibit optical isomerism. Which one does not have, will not exhibit optical isomerism. Okay, first of all, what is the formula of malic acid? CH, double bond CH, COOH and COOH. So here there is no chiral carbon, there is a double bond here. Therefore here this carbon is not bonded to 4 different groups. Therefore this cannot be a chiral carbon. And in COOH, C double bond O. So therefore this also cannot be a chiral carbon, because they cannot be bonded to 4 different groups when double bond arise. Therefore malic acid is not having a chiral carbon. Therefore it cannot exhibit or it does not exhibit optical isomerism. So this is correct. Then alpha amino acid, what is the formula of alpha amino acid? RCH NH2 COOH. So here it is having a chiral carbon. One is bonded to R, the other one is bonded to, so this hydrogen, you can write it as hydrogen, and this is NH2, this is COOH. Therefore it has a chiral carbon, therefore it exhibits optical isomerism. Therefore this cannot be the answer. And lactic acid also, so hydrogen, one methyl group and one OH group and one COOH group. So this is also having a chiral carbon, therefore this also does not exhibit optical isomerism. What about tartaric acid? So tartaric acid also, so C, H, COOH, OH, and here also you can write H, OH, COOH. So here it is having two chiral carbons. See, this carbon is bonded to 4 different groups. This carbon is also bonded to 4 different groups. Therefore it is having two chiral carbons. Therefore this is also having a chiral carbon. Therefore this also exhibit optical isomerism. Therefore here it is not correct answer, because they are asking which one does not exhibit. Therefore malic acid is the correct answer. Therefore option A is correct. Okay, you have to know the formula, then how to find out the chiral carbon for each and every type of compound. Only then this type of question can be answered. Therefore it is better to learn the structural formula of various acids in our syllabus. Hope you understood and it's very clear to you. Consider the reactions. So we are given two reactions here. Number one is isobutyl bromide, ethanol. Gives some ether compounds here. It gives some ether compounds plus HBr. And second one also the same reactant, but the reagent is different. That is C2H5O minus alkoxide ion. But the product is same and the other byproduct is Br minus. The mechanism of reactions 1 and 2 are respectively. So easy to find out. So here both are primary halogen compounds, CH2Br, CH2Br. So both will undergo SN2 reaction only. This is SN2, this is also SN2, because both are primary. How can you say it's primary? Bromine is bonded to this carbon, which is having 2 hydrogens. Therefore it is primary. So it is having 2 hydrogens. Same thing, the second reaction also, bromine is bonded to a carbon which is having 2 hydrogens here. Therefore this is also primary. Generally primary halogen compounds undergo SN2 reaction. Therefore option C is correct. Moreover, if it is SN1 reaction, so the intermediate carbocation would have formed. So here the carbocation is not shown, and it is shown it is taking place in a single step. Therefore it could be only SN2 reaction. Hope you understood it clearly. Which of the following compounds undergoes nucleophilic substitution reaction mostly? Okay, here all of them are aromatic compounds, aryl compounds, and chlorine is directly bonded to benzene ring. So let us take option D. So we have already learnt. So here chlorine is having 6 electron, 3 pairs of lone pair of electron, 3 lone pairs of electrons. Therefore what will happen? It is in resonance with the 3 pi bonds in benzene ring. Therefore this forms, okay, here it becomes minus charge, and then again this will shift here and it becomes minus, and then again this will shift here, this will become minus. Okay, so therefore here it is resonance stabilized, and moreover the bond between chlorine and the benzene ring become partially double bond. Therefore it becomes stronger. Therefore it will not undergo nucleophilic substitution reaction easily. So that is the case when chlorine is directly bonded to benzene ring. Therefore D is ruled out. So question is, which one will undergo nucleophilic substitution reaction most easily? So here compound D will not undergo very easily. So what about the other compounds? See, along with chlorine, one more substituent is there. Here in option A, NO2 substituent is there, and in option C, methyl is there, and in option B, methoxy is there. Therefore, in such cases, what will happen? No? We have to find out whether they are electron donating group or electron withdrawing group. Here, a nitro group is electron withdrawing group. Electron withdrawing group. So they will pull electron towards itself. Therefore, it will be easy for chlorine now to go away. Okay, if you take methyl group, so methyl group is electron donating group. So therefore, this chlorine will not be easily removed from this benzene ring. Same thing here, OCH3 also electron donating group. Therefore, this also will not release chlorine very easily. Therefore, it is tough to hydrolyze. Therefore, option A is correct. But now, one question will be popping up in your mind. How do I know which one is electron withdrawing and which one is electron donating group? So this is electron withdrawing group, and these two are electron donating group. Electron donating group. How do you know, or how can we find out? One simple clue I give you, most of the time it may be correct. So anything which is bonded here along with benzene, if it has a double bond in it, see NO2 can be represented like this. So it has a double bond in it. Therefore, it will be electron withdrawing group. In CH3, everything is a single bond. Therefore, it will be electron donating group. In OCH3 also, so everything is single bond. Therefore, this also will be electron donating group. So this may be helping you to find out whether it is electron withdrawing group or electron donating group. Therefore, here, which one will undergo the nucleophilic substitution reaction most easily? Option C, because nitro group is bonded to benzene, which is an electron withdrawing group. So that will help chlorine to get hydrolyzed easily in compound A. Hope you have understood it very clearly. Which is the most reactive towards SN1 reaction? See, in SN1 reaction, so we know it proceeds by, say, any substrate. When it undergoes SN1 type of reaction, the intermediate is carbocation. So whichever compound produces the stable carbocation will be most reactive. So now we have to see among these four options given, which one will form more stable carbocation. Okay, let us take the first one, C6H5, that is phenyl, then CH, and another phenyl, and then Br. This is compound A. And what is compound B? C6H5, CH, then CH3, Br. Okay, then what is compound C? Phenyl, and then it is carbon, then CH3, and then another phenyl ring, and then Br. Then what is the fourth one? D, benzene, that is phenyl ring, CH2, Br. Okay, now let us, now we have got a clear picture of these four compounds. Now let us try to think, analyze, and we'll try to find out which one will form more stable carbocation. See, generally tertiary halogen compounds only undergo SN1 type of reaction. You take option D. Here bromine is bonded to a carbon which is having two hydrogens. Therefore, this is a primary halogen compound. Therefore, this may not be most reactive towards SN1. Okay, all the other, see, if you take the first one, so here Br is bonded to this carbon which is having only one hydrogen. So this is secondary carbon. Okay, then what about the third one, option B? Option B is also, here bromine is bonded to carbon which is having hydrogen. Therefore, this is also a secondary carbon. And what about the option C? So bromine is bonded to a carbon which is having no hydrogen at all. Therefore, this is tertiary carbon. Tertiary halogen compound. Therefore, this only will undergo SN1 reaction very easily. That is, compound C is the most reactive towards SN1 reaction. So we can see in other way also. Suppose the bromine goes away and the carbocation is formed. So here, so the two phenyl groups are plus R groups. That is, they can donate electron towards the carbon positive because they are electron rich here. The pi electrons are delocalized, so they are free to donate its electron to the positively charged carbon. And methyl group also electron donating group. Therefore, this positive charge will be minimized here in the center. Therefore, this is more stable. Whereas in compound A, only two phenyl groups are there to act as plus R effect. No, only two phenyl groups. And here, if you take the second one, methyl group, that is inductive effect, that will push the electron towards the carbocation, and then phenyl group also will push their pi electron towards the carbon cation or carbocation. Thereby, the positive charge will be minimized. But here there are only two groups here. Here also only two groups. But in compound C, what is there? Two phenyl group and one methyl group. So two phenyl groups are plus R effect, and CH3 is plus I effect. So therefore, here the positive charge will be more stable in compound C. Whereas in option D, only one phenyl ring is there. So therefore, only one plus R effect. Therefore, here the positive charge may not be minimized that much. So therefore, this may not be stable here. So therefore, option C is the correct one. So you can simply find out which one is a tertiary halogen compound. That only will form stable carbocation. So that will be most reactive towards SN1 reaction. That is more than enough. So among the four options given here, option C is having tertiary carbocation. So that is why that is the correct answer. So if anybody asks you, okay, how do you prove or how do you know that tertiary carbocation here in option C is more stable? So because the carbocation is bonded to two phenyl ring and one methyl ring. So two phenyl rings are due to plus R effect, they are pushing their electron towards the positive carbocation. And methyl group also pushes its electron towards this positive carbocation due to plus I effect. Therefore, the plus charge will be minimized. Therefore, this carbocation becomes more stable. So that could be the reason for the more stability of tertiary carbocation. Hope you understood it very clearly. The correct order of increasing reactivity of CX bond towards nucleophile in the following compounds is. So they are given four options. Two are aromatic, first and two are aromatic compounds, and third and fourth options are aliphatic compounds. See, what we know is whichever forms stable carbocation, so that will undergo the nucleophilic substitution reaction very easily. So that can substitute the halogens in the halogen compound very easily. Okay, if you take option 1, so here halogen is directly bonded to benzene ring. See, already we know, so these halogens having 3 electron pairs here, that will be the electron pairs will be in resonance with the pi electrons in benzene ring. Therefore, one can move here and this can come here and this moves here and this moves here. Okay, they are in resonance. Therefore, there will be a partial double bond between the halogen and the benzene ring. Therefore, it is very tough to break. So that is why the CX bond in aromatic halogen compound, that is aryl halogen compound, that is the halogen directly bonded to benzene ring, are not more reactive, they are less reactive. Okay, now you take this one, option 2. So this is also aryl halogen compound, that is the halogen is directly bonded to benzene ring. The halogen is directly bonded to benzene ring. Therefore, the same effect will be there. But at the same time here, you are seeing that two nitro groups positioned at ortho position and para position. These nitro groups are what? Electron withdrawing groups. Therefore, they will pull electrons towards itself. They are electron withdrawing group. Therefore, the X can be easily removed than the first option. So this is also aryl compound. Therefore, there will be a partial double bond character between benzene ring and the halogen compound here. But however, due to the presence of electron withdrawing group like NO2 group. So the electrons will be pulled towards NO2 group. Therefore, the X will be loosely held to benzene ring than the first one. Therefore, option 2 will be more reactive than the first one. Okay, what about the third one? So here it is a tertiary halogen compound. Halogen is bonded to a carbon which is having no hydrogen. Therefore, this is tertiary halogen, which is more reactive or more stable. This carbocation formed from the tertiary halogen compound will be more stable. And what about the option 4? Halogen is bonded to a carbon which is having only one hydrogen, therefore it is secondary halogen compound. So the carbocation formed from the secondary halogen compound will be less stable than the tertiary halogen compound. Therefore here the compound 3 will be more reactive than compound 4, that is secondary. The first and second are okay, among these two, which is more reactive? Second one is more reactive and then the first one. But here what they are asking? They are asking the increasing reactivity. Therefore, we have found out in decreasing order here. Now that should be in the reverse order. Therefore, compound 1 will be less reactive than 2. That will be less reactive than 4. That will be less reactive than 3. So that is where that is present in the option A. Therefore, option A is the correct one here. Hope you understood it very clearly. See, tertiary halogen compounds will form a carbocation that is more stable than the carbocation formed from the secondary halogen compound. So, which is more stable than the carbocation formed from aryl halide compounds. But in aryl halide compounds, along with the halogen, if any other electron withdrawing group like NO2 is attached to benzene ring, then that will be more reactive than the plain aryl halogen compound. So if you know this order, and you can easily answer not only this question, any type of this question which is based on this pattern. Hope you understood everything clearly. In the following reaction, C6H5CH2Br, that is benzyl bromide, first treated with magnesium in the presence of ether, followed by H3O+, that is with water in the presence of acid. And you are getting X. The product X is, okay, so this is a halogen compound, therefore we should know the reaction between this halogen compound and magnesium in the presence of ether. So this is, what is phenyl, or this is benzyl. So this is benzyl bromide. When this is treated with magnesium, when it is treated with magnesium in the presence of ether, we all know what is formed. Grignard reagent is formed. That is, this Mg will be bonded between the CH2 and Br. Therefore, we will get benzyl magnesium bromide Grignard reagent we get. Okay, then this is treated with water. So this is step 1. And in the second step, what we get? When Grignard reagents are treated with water in the presence of acid, what we know? Alkane is formed. So here what will you get? So when it is treated with water, HOH, in the presence of water, what will happen? This hydrogen will be bonded to this carbon and this OH will be bonded to this magnesium. Therefore, what do you get? MgBrOH. And what alkane you will get? This hydrogen will be bonded to this CH2 and thereby it becomes CH3. Therefore, this is nothing but toluene. So what is this formula? So here they are given it in the form of formula. Therefore, the formula is C6H5. That is what is the phenyl ring. Then bond CH3. So this is nothing but toluene. So here compound C, that is option C, is the correct answer. So you should know the properties of Grignard reagent. So there are about 10 properties of Grignard reagent, and one of them is how Grignard reagent is converted into alkanes. So here first of all, how it is prepared? It is prepared from halogen compound by heating or by distilling with magnesium in the presence of ether. We will get Grignard reagent. When Grignard reagent is treated with water, we get the respective or the corresponding alkane. So here it is toluene. So if you know all the properties, this type of questions can be easily answered. So at least one question will be asked every year. Therefore, it is better to learn all the 10 properties of Grignard reagent, both for aliphatic and also for aromatic. They are similar and the reagent used as same, therefore it will be easy to learn and remember. Hope you understood this clearly. Which of the following reactions is an example of nucleophilic substitution reaction? So we have to be very careful here. Nucleophilic substitution reaction. So the attacking reagent should have a nucleophile. So like say let us say Y minus or any nucleophile minus. So it should have a nucleophile. Only then we can call it as nucleophilic substitution reaction. Okay, now let us take option A, Rx plus 2Na. Just by looking at this, you can come to know this is Wood's reaction. So two halogen compounds reacts with two sodium metal. So therefore what you get? NaX, NaX, 2 NaX you are getting, and this R will be bonded to this R. So this is Wood's reaction. Here there is no nucleophile. No, the Na is not having any nucleophile. Therefore, it cannot be nucleophilic substitution reaction. Okay, the second one, Rx, that is halogen compound. This is a substrate and hydrogen is a reagent. So this reagent, hydrogen, is not having any nucleophile. Therefore, this also cannot be a nucleophilic substitution reaction. So here X is replaced by hydrogen. You may think it's substitution reaction, but where there is a nucleophile. So here it may be considered as reduction reaction. So X is replaced by hydrogen. So removal of any electronegative element, addition of hydrogen is reduction reaction. Okay, in option C, Rx is Grignard reagent Mg. Here Mg is added between the alkyl group and the halogen. Therefore, this is addition reaction. And in option D, so here the reagent is potassium hydroxide, in which OH minus is a nucleophile. So that substitutes the halogen in the Rx group. Thereby you are getting ROH. Therefore, option D could be the nucleophilic substitution reaction. Hope it's very clear, and you have learned to think, how to arrive at the answer. That is more important. How we have to think from the given options and what is asked. So first of all, we need to find out what are given and what is asked, and what is the relationship between these two. On that angle, we have to think and derive the answer. Hope this is an example of how to think in an order. Okay, hope you understood it very clearly. How many stereoisomers does this molecule have? CH3, CH, double bond, CH, single bond CH2, single bond CHBr, single bond CH3. So since there is a double bond, there is every possibility of cis trans isomers. So therefore first you write CH double bond CH, or you write C double bond C, and you can write here hydrogen and CH3, and here you can write hydrogen and what are the other things? CH2, CH, Br, CH3. So this is cis isomer. C double bond C, and these are two hydrogens are on the same side, and the bulky groups are on the same side. Therefore, this is cis isomer. Like this, if you change one of the, see for example, if you change this is CH3 and hydrogen, and C double bond C and hydrogen, and the same bulky group here CH, Br, CH3. So here the hydrogens are in the opposite sides of the double bond, and then the bulky groups are on the opposite side. Therefore, it is trans. Therefore, cis-trans geometrical isomerism. There are two isomers here. Since it is having a double bond, definitely there is a possibility of cis-trans isomer. So there are two isomers. Then if it is having any chiral carbon, then that will exhibit optical isomerism also. So which carbon is having chiral? How to check? See here, first you take this carbon. This is having 3 hydrogen. Therefore, it cannot be, because all the 4 bonds should be bonded to different groups. And this carbon is having a double bond. Therefore, there is no possibility of all 4 different bonds. And this carbon is also having a double bond. Therefore, there is no possibility of chirality. Okay, the next one, carbon which is having 2 hydrogens. Therefore, 2 bonds are bonded to the same group. Therefore, this also cannot be. And this carbon also cannot be chiral because it is having 3 hydrogens. So the only option is only this carbon. You see, you take this carbon, one is bonded to hydrogen, the other one is bonded to bromine, the other one is bonded to the CH3 group, the other one is bonded to the remaining, the bulky alkyl group here. Therefore, only this carbon is chiral here. So all the 4 bonds are bonded to different groups. So if you write separately, you can find out CH, Br, CH3, and this side it is CH2, CH, double bond, CH, CH3. Now you can very well see all the 4 bonds are bonded to different groups. Therefore, this carbon is chiral. How many chiral carbons are there? Only one chiral carbon. Therefore, the number of possible isomer is 2 to the power n. So n is the number of chiral carbons. So here how many chiral carbons are there? 1. Therefore 2 to the power 1 is 2. Therefore 2 optical isomers and 2 geometrical isomers, cis trans isomers. Therefore 2 plus 2 is equal to 4 isomers. Therefore which option is correct? Option C is correct. So generally when people ask how many stereoisomers, immediately they check whether any chiral carbon is there or how many chiral carbons are there, and by using this formula they will find out. And they always forget about the geometrical isomers. If there is a double bond anywhere in the compound, there is a possibility of cis trans isomers, and that we have to be very, very careful. So most of the people will answer here option B. We have to take into consideration of geometrical isomerism also, that is cis trans isomerism. There are 2 and then 2 optical isomerism, therefore 4, therefore option C is the correct one. Hope you understood this very clearly. In a SN2 reaction of the type, okay, they given RBr plus Cl minus DMF gives RCl plus Br minus. Which one of the following has the highest relative rate? So they given it the SN2 type of reaction. So in SN2 type of reaction, we should know the order. So methyl halide will be faster than primary halogen compound, that is RCH2X, and which will be relatively faster than the secondary halogen compound, that is R2CHX, which will be relatively faster than tertiary halogen compound. So very easy to answer if you know this order very clearly. Suppose it is SN1 reaction, it should be, the order should be the reverse of this one. Tertiary halogen compound will be faster and methyl halide will be the slowest. Okay, in SN2, methyl halide will be the fastest and primary will be next fastest and secondary halogen and tertiary halogen respectively. Okay, now let us try to find out from the given option. See option A, here it should be Cl. Okay, Cl is bonded to this carbon which is having no hydrogen, therefore this is tertiary. So this will be the slowest here as far as SN2 is concerned. Okay, here Br is in option, okay, we take option B here. In option B, this is bonded to a carbon which is having 2 hydrogen, therefore this is primary. And option C, Br is bonded to a carbon which is having 2 hydrogen, therefore this is also primary. And you take option D, Br is bonded to this carbon which is having 2 hydrogen, therefore this is also primary. So now how to choose which one is the fastest among these 3? So A is ruled out because that is tertiary. Okay, in all the other 3 options, they are all primary halogen compounds. How to choose this one? See here, we need to understand another simple rule, that is in SN2 reaction, small groups on the carbon atoms attached to halogen are favored. See here, bromine is bonded to this carbon and which is attached to only methyl group. This is having only 1 carbon. Whereas here bromine is attached to this carbon which is in turn is attached to ethyl group. So which is having 1 carbon more than the previous one. Therefore B will be faster. Smaller the alkyl group bonded to the carbon which is directly bonded to the benzene ring, faster will be the SN2 reaction. Clear? See, bromine is bonded to this carbon and which is bonded to how many carbon groups? Only 1. And whereas in option C, Br is bonded to this carbon which is bonded to another alkyl group having 2 carbons. Therefore this will be slower than option B. And what about option D? So bromine is bonded to this carbon which is bonded to another bulky group, that is isopropyl group, which are having 3 carbons. Therefore, since option B is having only 1 carbon bonded to the carbon which is bonded to the bromine, so that will be the fastest. Smaller the alkyl group bonded to the carbon which is bonded to the halogen directly, faster will be the SN2 reaction. So you make this point, remember this point, so that will help you to answer any of this type of questions. Therefore, option B is the correct answer. Hope you understood it clearly. If there is no rotation of plane polarized light by a compound in a specific solvent, though to be chiral, it may mean that. So here they are given though to be a chiral. So it is a chiral compound, they themselves have given it. Therefore here if you look at the option, so it's a statement question. It's a very simple to answer. So though to be a chiral compound, so it is a chiral compound. Then in option they are given the compound is certainly a chiral. See, already they are given it in the question. Therefore this option may be ruled out. And second one, you take option C, the compound may be a racemic mixture. But in the question they are given, if there is no rotation of plane polarized light by a compound. So here they are given by a compound, therefore it cannot be a racemic mixture. So they are given only by a compound, so how can it be a mixture? Therefore option C is also ruled out. So there is option B is there is no compound in the solvent, the compound is certainly meso. So here for optical isomerism, we have to see whether it is meso or not. For example, if I give you tartaric acid, H, OH, here it is COOH, and here there is a carbon, here there is a carbon. So here these two carbons are chiral carbon because this carbon is bonded to COOH, OH, H and carbon, 4 different groups. Therefore this is a chiral carbon. Similarly this carbon also attached to 4 different groups. Therefore this is also a chiral carbon. So even though there are 2 chiral carbons, it is not rotating the plane polarized light. Why? Because if you split the compound into 2 here, so the one half of the tartaric acid, this one half, this is the upper part of the tartaric acid, is exactly the mirror image of the second half of the tartaric acid. That means what? There is plane of symmetry. So when there is symmetry, the rotation will be nullified. For example, the upper part might rotate the plane polarized light. For example, you take this compound, you pass a plane polarized light towards it, the upper part will deviate to the right hand side. To the same extent, the bottom part will deviate to the left hand side. Since the deviation is equal, so these deviations are nullified and there is no it shows no deviation in the plane polarized light when the compound is mesotype. That means what? If one half of the structure is the mirror image of the other half of the structure, then it is having plane of symmetry. That means what? It can nullify the rotation of each part of the compound to 0. That is why it is not deviating the plane polarized light. Hope it's very clear to you. So such type of questions can be very easily answered if you are very thorough with the concept, because it is all statement questions. So very easy to answer. We can solve it very quickly also. We can save lots of time here. Hope you understood it clearly. CH3, CHCl, CH2, CH3 has a chiral center. So they have given it very clearly. It has a chiral center. Which one of the following represents its R configuration? So what is meant by R configuration? So if the preferred groups in any optical isomer compound is in the clockwise direction, if they are arranged in the clockwise direction, that is R configuration. If they are arranged in the anti-clockwise or counterclockwise direction, that is S configuration. So clockwise is R configuration, counterclockwise, that is S configuration. So what is the preferred group? How to choose that preferred group? See here they are given it is having a chiral center. See in all the options A, B, C, D, the central carbon is the chiral carbon because they are attached to 4 different groups. See here this carbon is bonded to C2H5, CH3, ClH. So all 4 groups are different, therefore this carbon is chiral. That is the same with all the other options also. Okay, now how to prefer the groups bonded to the carbon atom, chiral carbon. So whichever is having more atomic number bonded to the carbon should be preferred first. See, chlorine atomic number is 17, carbon atomic number is 6. Here also the carbon atomic number is 6. The hydrogen atomic number is 1. Therefore, chlorine will be A. This is the first preferred because it is having highest atomic number among these 4. And hydrogen will be the least, therefore that will be D. Now if you take the other two, both are carbons, both are having atomic number 6. Therefore which one should be preferred? So we have to see the next atom bonded to that. So here this carbon is bonded to 3 hydrogens. So they are all having atomic number 1 only. Here it is C2H5. C2H5 means it is nothing but what? CH2 bond CH3. So this carbon is bonded to 2 hydrogen and then it is bonded to another carbon. So which is having atomic number 6 and these 2 hydrogens are having atomic number 1 only. Therefore this C2H5 is preferred to this CH3 because 2 carbons are there. The carbon bonded to the next carbon having more atomic number. Here only hydrogens are bonded which is having less atomic number. Therefore C2H5 is preferred to CH3. Therefore C2H5 is B and CH3 is C. Hope you understood this very clearly. Okay. Now we need to find out whether it is A, B, C. See, we have to see from A how it is moving to B, how it is moving to C. Ignore D. Ignore D altogether. Okay. So now you take A, chlorine, and B is C2H5 and CH3 is C. Okay. Now this chlorine, A and B and C. Therefore it is moving in which direction? Which is moving in clockwise direction. But still yet it is not R configuration because it is crossing H. If it is crossing H, if it is moving in the clockwise direction, you have to consider this as anti-clockwise. Therefore if you consider this as anti-clockwise, that is S configuration. Therefore this is wrong. Now you take option B. You take chlorine. A is chlorine and C2H5 is B and CH3 is C and hydrogen is D. Okay, now you move A to C, A, B, C. This is also moving in clockwise direction, but it is not crossing the least preferred hydrogen. Therefore this is R configuration. Okay, therefore B could be the correct answer because they are asking in the question what is the R configuration. Okay, now let us see C. Okay, which is A, chlorine is A, C2H5 is B and CH3 is C. Now you move from A to C, A, B and then C. So this is also moving in clockwise direction, but it is crossing the least preferred hydrogen. Therefore R should be considered as the reverse of that. Therefore S. So S means what? That is traveling in the anti-clockwise direction. Therefore this cannot be correct. Okay, then option D. Chlorine is A, this is B and this is C. So A to C, this is moving in the anti-clockwise direction, therefore S configuration. Of course it is not crossing H, therefore that should be considered as S only. Therefore this also cannot be correct because we want R configuration. So therefore which is the correct answer? Option B is the correct answer. So even though the preferred order is moving in the clockwise direction in option A, see option A here, option B here, option C here, it is moving in the clockwise direction, but still it is not considered as R configuration because it is crossing the least preferred hydrogen. Therefore if it is traveling in R, we have to consider this as S. If it is traveling in clockwise, we have to consider this as anti-clockwise. Therefore this is S configuration. So in option B, it is moving in the clockwise direction. Of course it is not crossing H. Therefore it is R configuration. In option D, it is moving in the anti-clockwise direction. Therefore it is S. Of course it is not crossing H. Therefore no problem. Okay, then in option C, it is moving in R direction, that is clockwise direction, but it is crossing H here. Therefore that should be considered as S configuration. Hope it is very easy for you to identify now which is R configuration and which is S configuration. Which of the following is not chiral? See here you have to be careful, not chiral. Therefore now we have to see all the 4 options and we have to find out one by one. So let us take compound A, 2-hydroxypropanoic acid. So first of all, what is chiral? A compound should have a carbon which is bonded to 4 different groups. So for example, here it is A, B, D and E. See, if all the 4 groups bonded to a carbon atom are different, then this carbon is said to be chiral. If any 2 groups are same, it cannot be a chiral. Here we need to find out which one is not chiral. We have to be very, very careful. Okay, now let us take the first compound for option A, the 2-hydroxypropanoic acid. 1, 2, 3 propanoic acid and 2-hydroxypropanoic acid. Therefore the other bonds, so here it should be bonded to hydrogen and here it should have 3 hydrogens. So this carbon is bonded to 4 different groups, OH, COH, H and CH3. Therefore this is having a chiral carbon. Therefore this is not the correct answer. Second one is 2-butanol. So but, therefore it should have 4 carbon and then 2-butanol, therefore it should be OH. Therefore if you complete it with hydrogen, CH3 here, it is CH and here it is CH2, here it is CH3. So this carbon is again chiral. See, it is bonded to hydrogen, methyl, hydroxy and ethyl group. Therefore this is also a chiral carbon. What about the third one? 2,3-dibromopentane. It is pentane. Therefore first you write 1, 2, 3, 4, 5 carbons and everything is single bond because it is ending with the N, pentane. And 2, 3, suppose you start from here, the second carbon and third carbon bromine should be there. 2 and 3 bromopentane. Okay, now it should be CH3, it will be H and this also will be H and this will be H2 and H3. Okay, if you take this carbon, so this is bonded to hydrogen, ethyl, bromide and another group here. And similarly if you take this carbon, this is bonded with hydrogen, methyl, bromide and the other group. Therefore there are 2 chiral carbons here. Therefore this cannot be not chiral. So it is a chiral compound. Therefore option C is also ruled out. See, already we have ruled out B and now C is also ruled out. Therefore without testing we can conclude option D should be the correct one. But anyway, let us check here. 3-bromopentane. So pentane, so it should have 1, 2, 3, 4, 5 carbons and in the third carbon bromine should be there, therefore Br. Therefore, so it will be CH3, CH2, here it is CH, it will be CH2, CH3. You take this carbon, here it is bonded to hydrogen, here it's bonded to bromine, this side it is bonded to ethyl, this side also it is bonded to ethyl. These 2 groups are same, therefore this is not chiral, it is achiral. It is achiral, therefore option D is the correct one. Hope things is very clear to you. Which of the following undergoes nucleophilic substitution exclusively by SN1 mechanism? So if you know the order of the carbocation, it becomes much easier here. So SN1 reaction follows 2 steps. In the first step, carbocation is formed. So the step, it depends on the stability of the carbocation. The order of stability of the carbocation is first benzyl. So benzyl carbocation is more stable than allyl. So what is allyl? CH2 double bond CH. Okay, this is allyl. And which is more stable than tertiary halogen, tertiary carbocation, and which is greater than secondary carbocation, which is greater than primary, which is greater than methyl. So methyl halogen maybe, or CH3 plus. Okay, so this is the order for SN1 reaction. This will be the reverse order for SN2 reaction. Already we had seen for one of the SN2 types of reaction in the reverse order. Here now we have to see in the different order. So what is ethyl chloride? C2H5Cl. What is isopropyl chloride? CH3CH, CH3Cl. And what is chlorobenzene? Okay, this is benzene. Okay, this is chlorobenzene. Then benzyl chloride. What is benzyl chloride? CH2Cl. Okay. So here, so which one will be more stable? The one which is bulky in nature, the carbon which is bonded to the halogen, and this other side it is bonded to the benzene. So this is whichever is bulky in nature, the bulky group which is bonded to a carbon which is the other way bonded to the halogen atom. So whichever is bulky here, so that will be more stable, so that reaction will be favored. See, among these four, which is bulky? So this is what is bulky here. And here in option C, so due to resonance, it is more stabilized, no? So here the partial double bond will be there between chlorine and benzene. Therefore, this reaction is very tough here, even though this phenyl ring is also bulky, but here the reaction is very slow, slower than the alkyl groups because of the partial double bond character between chlorine and the benzene. Therefore, here the fastest will be the one which will undergo exclusively SN1 mechanism will be benzyl chloride, because this forms benzyl cation. Benzyl cation is more stable than allyl cation. Allyl cation is more stable than tertiary, and then secondary, then primary, and then methyl group. So therefore, anything having benzyl cation, anything forms benzyl cation will be more stable. So therefore, option D is the correct answer. Hope you understood it clearly. The chirality of the compound. So they are given this compound. It is here very clearly given in wedge dash form. So that is bromine, this carbon, and this CH3 are on the plane. So Br, carbon, and CH3 are on the plane. Okay, maybe plane on the board. And this is showing it is going backwards. Hydrogen is going at the back side of the board. And here chlorine is projecting towards us. It is projecting towards us. It is given in the form of wedge. Okay, it is given in the form of wedge. That is, so the bromine and CH3 with a normal line are on the plane of the board, and carbon hydrogen, the hydrogen is projecting backward of the board, back side of the board, and then this carbon chlorine bond, no, that is projecting towards us in front of the board. So that's what we need to understand. So now we have to choose a priority. So what is the atomic number of bromine? Bromine atomic number is 35, chlorine is 17, hydrogen is 1, and this carbon is, what is the atomic number, is 6. So therefore, what is the priority here? So bromine is A, and chlorine is B, and carbon is C. So the low priority hydrogen is projecting backwards. So when it is projecting backwards, we need not bother about that. So we can leave out that, and now we can see how it moves. So A is moving to B and then to C. It is moving in the clockwise direction. Therefore, the configuration, it is R configuration. The configuration is R because it is moving in the clockwise direction. But you might ask me, sir, in question number 28, you said when the line is crossing the hydrogen, then we have to change R to S and S to R. But only that is shown in the form of 2 dimensions. So there in question number 28, it was given like this. Hydrogen, the priority A was here, and B was here, and C was here. So it is given in 2 dimensions. Therefore, when it is moving here, it is crossing the low priority hydrogen. That is why we change when it is moving in the clockwise direction, it is R, but that should be considered as S. But here it is given in 3 dimensions. So that is hydrogen is at the back side. Always the lower priority is at the back side. We have to take as it is. So here hydrogen is the lowest priority. So it is pointing backwards. Therefore, we have to take exactly the same order. See, A, B, C is moving in the clockwise direction. Therefore, it is R. Therefore, it is R configuration only. So if you want, you go back and see question number 28. There the structure is given in 2 dimensions. See, hydrogen is not shown backwards or at the back side of the formula. But here it is very clearly indicated, no, with the dash. So hydrogen is projecting backwards, back side of the board. Therefore, here we should not consider whether the clockwise and anti-clockwise direction is crossing that hydrogen. We are least bothered when it is shown in the form of dashes. That is when hydrogen is projecting backwards. Clear? Hope you have understood it. If you want, you can go back and see the question number 28 again and compare these two so that it will be easy for you to remember very well. So therefore, here it is R configuration. Therefore, the answer is A. Hope you have understood it clearly. Which of the following is least reactive in a nucleophilic substitution reaction? So it may be SN1 or SN2, we are least bothered. So nucleophilic substitution reaction they are given. All of them are halogen compounds. Now we have to see one by one. So this is a tertiary halogen compound, CH3, 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 Cl. So it can form a stable tertiary halogen compound, or it can form stable tertiary carbocation. So which is more stable, therefore it can readily undergo the substitution reaction. Whereas you take option B, CH2, that is vinyl chloride. Option B is vinyl chloride, CH2, CHCl. So here this chlorine is having 6 electrons, that is 3 pairs of electrons. So this electron pair is in conjugation with the double bond here. Therefore this will be shifted here, and this 2 pi electrons will be shifted here. Therefore it will be in resonance with this structure. Therefore CH2 minus, so this becomes single bond, CH double bond. What is this? Here also double bond, that becomes Cl. Here the chlorine becomes partially positive. So when it becomes partially positive, it cannot undergo nucleophilic substitution reaction. For the substitution to take place, the chlorine has to gain back the 2 electrons which it has lost in the resonance. Therefore, and partial double bond character is there between carbon and chlorine, which is stronger than the single sigma bond. Therefore it is tough to break, therefore it is tough to undergo nucleophilic substitution reaction. So the reason is due to resonance stabilization. Okay, therefore this could be one of the answers, but let us check the other answers also. In compound C, here chlorine, therefore here what will you get? So it will form primary carbocation, so which is less stable than tertiary. Therefore the reaction will be slower here. And what is the last one? D. And here also chlorine. So it is also a primary halogen compound. Therefore this also can form primary carbocation, CH2 plus. Okay, so tertiary can undergo faster and primary can undergo a bit slower than the tertiary. But whereas in option B, there is no easy substitution reaction due to resonance stabilization. So you might ask me, sir, here also there is a double bond, there is chlorine. Why not it be resonance stabilization here? So here CH2, CH, CH2, Cl. Okay, here chlorine. So due to inductive effect, it pulls this electron and it becomes partially negative. And here there is no double bond in this carbon. It is not bonded to sp2 hybridized carbon. Here it is sp3 hybridized carbon. It is sp3 hybridized carbon. Therefore here there is no resonance here. So if there is a double bond here, then it will be in resonance with chlorine. But this is allyl chloride, no? This is allyl chloride. So in allyl chloride there is no resonance like in vinyl chloride. Therefore it can easily form primary carbocation. But whereas in vinyl chloride, due to resonance, this is more stable. Therefore the carbon chlorine bond becomes much stronger, and therefore it is not easy to break. That is why vinyl chloride will not undergo nucleophilic substitution reaction so easily. Therefore the option B is the correct one. Hope you understood it clearly. Which of the following pairs of compounds are enantiomers? See, for enantiomers, what it should be? It should be mirror images of each other. Both the compounds should be mirror images. Mirror images of each other. This is the first condition. And second condition should be non-superimposable. Non-superimposable. So what does that mean? So now you take option A. So compound A should be mirror image of compound B, or the other way. So let us see here. Suppose that this is A and this is a mirror image here. So CH3, CH3 here, OH, OH here, and hydrogen here, and far away hydrogen here. And hydrogen are close to each other. Then OH and OHs are far away. And here it is CH3. Therefore, it is exactly the mirror images. And what is the second condition? Non-superimposable. Non-superimposable means what? You take one of these compounds, that is, you take compound B here, and you place it on A. If they are all the same, all the groups are same, then it is superimposable. Otherwise it is non-superimposable. See, if you keep on this, if you keep B on A, so CH3 will come. Here it is OH, here it is H. Here it is H, here it is OH. Here it is H, here it is OH. Here it is OH, here it is H, here it is CH3. So these groups will be different. Therefore it is non-superimposable. See, first of all, these two compounds are mirror images and also non-superimposable. Therefore, option A should be enantiomers. For any pair of compounds to be enantiomers, these are the two conditions. What is the first one? They should be mirror images of each other. And second, it should be non-superimposable. Now let us check for the other pairs of compounds. You take option B here. So suppose there is a mirror in between these two. So here OH, here it is H, here it is H, here CH3. Here it is H, here it is OH. Therefore, it is not mirror image. Therefore, we need not go for the second option, non-superimposable. Here it is OH. See, here it is OH, here it is H. Therefore, it is not mirror image. Therefore, we need not go to the second option. It cannot be enantiomers. Okay, third option, again you put a mirror here. CH3. Here it is OH, here it is H. So it is not same. Therefore, it cannot be mirror images. Therefore, it is also ruled out. And option D, CH3. Here it is H, here it is OH. So it cannot be mirror images. Therefore, this is also ruled out. So it should be mirror image of each other, and one should be non-superimposable with the other one. Then this pair of compounds are called enantiomers. Therefore, here the option A is the correct one. Hope you understood it clearly. Reactivity order of halides for dehydrohalogenation, that is removal of HX, is RF, RCl, RBr, Ri. Okay, I think we have discussed in question number 1 the same thing. So if you want, you can refer back to question number 1 also. So RF, RCl, RBr and Ri. Okay, here bond strength depends on what? The size of the atom. See, RF. So fluorine is the smallest size among the halogens. Then chlorine, this will be slightly bigger. Then RBr, the bromine size is slightly bigger. Then Ri will be slightly bigger than that. This will be the biggest. Therefore, the bond length will be more as you go down the group. When the bond length increases, what happens? The bond strength decreases. Therefore, Ri bond strength is very less compared to RF. So therefore, the reactivity will be the reverse order. So when the strength is less here, it can be easily separated. Therefore, it can react faster. Therefore, Ri will be more reactive than RBr. RBr will be more reactive than RCl. That will be more reactive than RF. See here, bond enthalpy or bond strength depends on what? Size. Or what we can say. So bond length is depending on what? It is depending on the directly proportional to size. So when bond length increases, what happens? The bond strength decreases. When bond strength decreases, what will happen? It is very tough to break the bond between them. Therefore, it cannot be separated easily. Therefore, the reactivity will be less here. Whereas here, when the bond strength is weak, it can be easily broken. Therefore, the bond strength will be very less and it will be more reactive. Therefore, the correct order is Ri will be, so the bond length is more, and which is slightly less than that RBr, which is slightly less than this RCl. Then RF is the smallest. So therefore, this is more reactive. Therefore, what is the order here? B is the correct one. Ri is greater than RBr, is greater than RCl, greater than RF. But in question number 1, they would have asked a different way. So which is having bond enthalpy more? That will be the reverse of that. RF bond enthalpy will be more, because the energy required to break the bond will be more here, because that is stronger. Same question is asked in a different way. That's it. So you need to understand what is the relationship between bond length and then bond length and reactivity, and what is the relationship between bond strength and reactivity, and the relationship between bond, the size of the atom with bond enthalpy. These are the things, if you are very clear, you can answer any type of these questions or any pattern of this type of questions. Hope you understood it clearly. CH3, CH2, Cl, treated with NaCN gives X, which is further treated with nickel hydrogen gives Y, and that is further treated with acetic anhydride gives Z. So what is Z? So we need to find out Z in this series of reactions. So this is a halogen compound. It's treated with sodium cyanide. Therefore this will undergo substitution reaction with sodium cyanide. So cyanide is a nucleophile that will replace this chloride. Therefore what will you get? X will be CH3, CH2, Cn. Okay, so let me write it down here so that we can easily clearly understand this. CH3, CH2, Cl is treated with sodium cyanide. Okay, sodium chloride forms and cyanide replaces the chlorine. Therefore you will get CH3, CH2, C. Cn can be written as what? C triple bond N. That is cyanide. Okay, with the purpose I am writing this because when it is treated with nickel and hydrogen, so this is a reducing agent. So this supplies nascent hydrogen to this one. So where this hydrogen will go, wherever there is a multiple bond, there it will go. So if there is a triple bond here, therefore two hydrogens will go to carbon and two hydrogens will go to nitrogen, and thereby the triple bond becomes single bond. Therefore what will you get? CH3, CH2, and here you will get CH2 where two hydrogens are added here, and the triple bond becomes single bond and nitrogen, and two more hydrogens are added to this nitrogen. See, altogether how many hydrogens are required? 4 hydrogens are required. So which is supplied by Raney nickel. That is what is one of the reducing agents, nickel and hydrogen. Okay, now this is treated with acetic anhydride. Acetic anhydride is one of the acetylating agent. So what is compound Y we have got? So we have got propylamine or aminopropane. Aminopropane. Okay, now you take that compound CH3, CH2, CH2, NH2. So this is compound Y. This is treated with what? Acetic anhydride. What is the formula of acetic anhydride? CH3, CO, O, CO, CH3. This is an acetylating agent. That means what? So that will replace one of the hydrogens in the amine group with acetyl group. This is acetylating agent. So if you want to replace hydrogen with acetyl group, you can treat it with acetic anhydride anywhere in any other reaction also. So we need to understand this is acetylation reaction. And where this hydrogen will go? This hydrogen will go to CH3COO and forms acetic acid. This combines with this and forms acetic acid. Therefore the products will be what? So one is acetic acid. So the byproduct is acetic acid, CH3COOH. Now what is the remaining compound? You can write up to this, there is no change. We can write exactly the same thing. CH3, CH2, CH2, NH. Because one of the hydrogens combined with this acetate group forms acetic acid. Now only NH, that will be bonded to the acetyl group. You cannot combine this to CH3 because only this bond is broken. Therefore the CO should be bonded to NH. Therefore it is COCH3. So now we have to check which answer is correct in the option. So you take option A, CH3, CH2, CH2, NH, COCH3. Yes. So this is the same product we have got here. Therefore option A could be the correct one. So we are not getting here because there is no CO. Okay, therefore it cannot be. And here this NHCH3 is there. Therefore it cannot be. And here two CO groups are coming. Therefore it cannot be. Therefore only option A is correct one. Okay, hope you if you have learned the properties of halogen compounds, how they are treated with sodium cyanide, and when cyanide compounds are reduced, what happens, and then when amino compounds are treated with acetic anhydride, what happens. So they have combined 2-3 chapters. We have not yet learned, or you might not have learned about amino compounds and their properties. But you can very easily understand, if you understand acetic anhydride is acetylating agent that will replace one of the hydrogens in the amino group with acetyl group. You might ask me why it is not substituting any of the hydrogens in the carbon, why it is substituting only the hydrogen in the nitrogen. So here the amino group is a functional group. Why they are called functional group? Mostly they only will function in those reactions. That is why they are all called functional groups. So for this hydrogen to be substituted, that is hydrogen bonded to carbon, or to be substituted, special conditions are required. Otherwise normally only the hydrogen in the functional group only will undergo changes. Hope it's very clear. It helps you to solve many other problems as well. CH3, CH2, CHCl, CH3 obtained by chlorination of N-butane will be. This is secondary halogen compound. So here, which is obtained from N-butane. So what is N-butane? CH3, CH2, CH2, CH3. See, actually chlorination of any alkane, no, that will undergo free radical mechanism. So here it is treated with chlorine. So how the reaction takes place? So first chlorine split into two chlorine free radical, Cl one electron with another one electron, that is called free radical. Now, so this Cl free radical attacks the alkane CH3, CH2, CH2, CH3, and it forms secondary free radical. Only here this hydrogen will be removed and form secondary free radical ion. So therefore you will get one hydrogen from here will combine with one Cl forms HCl and CH3, and you will get CH dot. So this becomes free radical CH2 CH3. So now this is sp2 hybridized. When sp2 hybridized, the p orbital will be projecting up and down. So now therefore the next chlorine atom, next chlorine free radical can attack either from the upper side or from the bottom side. So it can attack from two different sides. Therefore we will get two different products. What are they? CH3, CH. Suppose it attacks from the upper side, chlorine will come here and then CH2, CH3. Okay, if it is attacked from the downside, you will get CH3, CH, Cl, CH2, CH3. So that means what? Here the hydrogen will be here, this hydrogen will be here. So the spatial arrangement differs. Therefore we will get only racemic mixture here. So therefore option B is the correct one. So how we can find out here? So when alkane undergoes chlorination, it follows free radical mechanism. So when free radical mechanism happens, so when this chlorine free radical attacks this butane, so why it is not forming free radical in the first carbon? Why it is forming in the second carbon? When it forms in the second carbon, it will be secondary. So secondary is more stable than primary. So that is why secondary free radical is formed. So which is sp2 hybridized. Therefore the p orbital will be projecting upward and downward, and the next chlorine free radical can attack from the upper side or bottom side. Therefore two options are possible. Therefore two different products we will get. That is why the racemic mixture is the correct answer. Hope it is very clear to you. An organic compound A C4H9Cl on reaction with sodium diethyl ether. So once we see this reagent, we should know it is going to be what type of reaction? Woods reaction. It should be Woods reaction. Gives a hydrocarbon which on monochlorination gives only one chloro-derivative. Then A is, so they are given four options. First it undergoes Woods reaction with sodium and diethyl ether, and then it which on monochlorination, that is that undergoes chlorination only one time, that is what is monochlorination. So what type of only one type of monochlorination takes place, then that means what could be the compound A. Okay, now let us take tertiary butyl chloride. So what is tertiary butyl chloride? CH3C, CH3, CH3Cl. Okay, treated with sodium metal in the presence of diethyl ether. So therefore here we take two sodium and another tertiary butyl chloride, CH3, CH3. Okay. So therefore what happens here? Two NaCl is formed, and then this carbon will be bonded to this carbon. Therefore what will you get? CH3, C, CH3, CH3, C, CH3, CH3, CH3 bond is formed. So this on chlorination, the two monochlorination. So why monochlorination? So only one product is formed here, they are given. Here all of them are CH3. No, all of them are CH3. Therefore wherever hydrogen is substituted by chlorine, that will be the same. So that will be the same compound. So therefore, here the answer could be only tertiary butyl chloride. We can easily find out. Luckily, we got it in the first option itself. Suppose we take secondary butyl chloride. So let us work it out. See, now we are getting it in the first time itself, in the first option itself. Therefore, there is no problem. Suppose we are not getting it, we have to go and we should learn to work out for the other given compounds also. This is secondary butyl chloride. What is secondary butyl chloride? CH3, CH2, CH, CH3, Cl. This is secondary butyl chloride. Okay, so if you subject it to Wood's reaction, what will happen? So this Cl to NaCl, like that, one more type of compound will go, and here you will get the same type will be repeated. No, that what will you get here? You will get CH, CH3, CH2, CH3. So here if you subject it to chlorination, here CH3 group is there, CH2 group is there, CH group is there. Therefore more than one type of chlorine compound will form. It will not be monochlorination. Okay, therefore option B cannot be correct. You take isobutyl chloride. What is isobutyl chloride? CH3, CH3, CH2, Cl. Again, when it is subjected to Wood's reaction in the presence of diethyl ether, what will happen? 2 NaCl will go away, and the same this group will be repeated here. CH2 bond, CH2, then CH, CH3, CH3. Again here also we are not only getting CH3 group, we are having CH2, CH2, and here it is CH is there. Therefore, the three types of chlorination will take place when we subject this to chlorination. Therefore, this option is also wrong. Then N-butyl chloride. What is N-butyl chloride? CH3, CH2, 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 Cl. When treated with sodium in the presence of diethyl ether, what will happen? So, two butyl group combine to form octane. So, in octane also, what will you get? CH3 group will be there and CH2 groups will be there. Therefore, more than one type of chlorine substituted compound will form. Therefore, option D is also wrong. So, only in option A, when it is subjected to Wood's reaction, we are getting this product. So, when we are subjecting it to chlorination, all of them are CH3 groups in the same place. Therefore, wherever it undergoes substitution, it will be the same product. Therefore, option A is the correct one. Hope you understood it clearly. A compound of molecular formula C7H16 shows optical isomerism. Compound will be, okay, it shows optical isomerism, they are given. Therefore, it should have a chiral center. At least one chiral carbon should be there. Now, from the given three options are given. Now, we have to check one by one. What is the first one? 2,3-dimethyl pentane. What is pentane? 1, 2, 3, 4, 5 carbons. All bonds are single bond, therefore AN. So 2,3-dimethyl. Suppose we start from here 1, and this is the second carbon. Therefore here it is methyl, and 3 also methyl. Okay, therefore CH3 it will be CH, CH, CH2, CH3. Okay, now let us take. So this cannot be a chiral carbon because 3 hydrogens are bonded, and here also this also this also. Let us take here. So this is bonded to 2 CH3 group. Therefore it cannot be. Now you take this one. So here this hydrogen we can take like here. So this is bonded to one hydrogen, one methyl, one ethyl, and then one isopropyl. Therefore this carbon is chiral carbon. This carbon is chiral carbon. This cannot be because 2 hydrogen, 3 hydrogen. Therefore this cannot be. At least one chiral carbon should be there. Therefore this compound A is having a chiral carbon. Therefore it exhibits optical isomerism. So luckily we got in the option A itself. Therefore this could be the correct answer. But let us check the other compounds also whether they have chiral carbon or not. So 2,2-dimethyl butane. So what is butane? 4 carbons and N. Therefore they should have a single bond, and 2,2. Therefore in the second position 2 methyl groups. So CH3, CH3. So CH3. Here there is no hydrogen. Here it is CH2. Here CH3. So here 3 hydrogens are there, 2 hydrogens are there, 3 hydrogens are there, 3 hydrogens are there, 3 hydrogens are there. Therefore it cannot be chiral carbon. Let us take this one. Here out of 4 bonds, 3 bonds are bonded to CH3. Therefore this also cannot be a chiral carbon. Therefore no chiral carbon in this. Therefore option B is ruled out. Then option C. So here since option A is having chiral carbon, then none of these also ruled out. Now 2-methyl hexane. So what is hexane? 6 carbon, 1, 2, 3, 4, 5, 6. Ane, therefore everything should have a single bond. And then 2-methyl. So in the second position there should be CH3. So therefore it is CH, here CH2, 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 CH3. So here more than one hydrogen is there. Therefore it cannot exhibit, it cannot show chirality here. Okay, but this carbon is having one hydrogen and one butyl group and two methyl groups. So these two methyl groups are same. Therefore this carbon is also not having any chirality. Therefore this option is also ruled out. Therefore option A is the only compound having a chiral center. Therefore this is the correct answer. Hope you understood it clearly. Which of the following compound is not chiral? Okay, now we have to write them separately and we have to check whether all four bonds are same or different. Okay, compound A, CH3. So whenever there is more than one hydrogen, we can write them together because it cannot be chiral. And then CHD, so H and D, that is heavy hydrogen. And then CH2 we can write together because more than one hydrogen, same group, therefore it cannot be chiral. And then Cl. So here this carbon is chiral because one is CH3, the other one is D, the other one is hydrogen, the other one is CH2Cl. See, all the four groups are different, therefore it is having a chiral carbon. Okay, but what they are asking, which is not chiral. Okay, therefore option A cannot be the correct one. Okay, then option B, you take CH3, CH2, because three hydrogen, two hydrogens cannot be chiral. Then C, H, D and Cl. Here this carbon is bonded to four different groups. Therefore this is also having chiral. But the question is what not chiral. Therefore option B is also not correct. Then option C. So D, CH2. Here two hydrogens are there in this carbon. Therefore we are taking it as it is CH2, CH2, Cl. So every carbon is having the same group more than once. Therefore it cannot be chiral. Therefore option C should be the correct one. So it is not having any chiral carbon. Option D, if you take CH3, then CH, Cl, then CH2D. So this carbon is having two hydrogen, therefore it cannot be, three hydrogen cannot be here. This carbon is having one hydrogen, one chlorine and CH2D and then CH3. All four groups are different. Therefore this is also having a chiral carbon. Therefore this cannot be the correct answer because they are asking which one of the following compounds is not chiral. We have to be very careful. Always we take for chiral. No? We take it for granted. Question is chiral, not chiral. Okay, we have to be careful. Many children make mistake in identifying this not. Okay, so here the answer C is correct, which is not a chiral compound. Hope it is clear to you and you have understood it very clearly. Replacement of chlorine of chlorobenzene to give phenol requires drastic conditions, but chlorine of 2,4-dinitrochlorobenzene is replaced readily because, see here what they are asking is, so here in order to substitute this chlorine to give phenol, that is when it is treated with sodium hydroxide under high temperature and pressure. So a drastic condition is required to replace this chlorine with OH group because this chlorine forms a double bond with the benzene ring due to the resonance. Therefore this bond becomes stronger, it cannot be replaced. But when this same chlorobenzene is substituted with dinitrochlorobenzene, see for example here in ortho position nitro and para position nitro, that is chlorine. So here they are given 1, 2, 3, 4. 2,4 nitro or 2,4 dinitrochlorobenzene. This is what is 2,4. The second and fourth position nitro group is there. 2,4 dinitrochlorobenzene. But when this is hydrolyzed with sodium hydroxide, such drastic conditions are not required. So why they are asking? Because this NO2 group is electron withdrawing group. We have seen in one of the questions before. So NO2 group is electron withdrawing group. So they will pull electron towards itself. Therefore it creates a positive charge in the ortho position and the para position that makes easier for chlorine to be separated from benzene ring. So therefore which option could be the correct one? So NO2 donates electron. No, it withdraws electron. So donates, definitely it cannot be. Then NO2 withdraws electron from ortho and para position. Okay, this is correct. Then NO2 makes ring electron rich at ortho and para position. No, no way it makes the ring electron rich, because it is pulling the electron from the ring. Therefore this is also wrong. Then NO2 withdraws electron from meta position. No, it is present only in ortho and para position. Therefore it can withdraw electron from the ortho and para position only. It cannot withdraw electron from the meta position directly. Therefore this is also wrong. Therefore option B is the correct one. So NO2 withdraws electron from ortho and para position, which makes the leaving group chlorine to leave the benzene ring easily. Hope the answer is clear and you have understood it perfectly. The alkyl halide is converted into an alcohol by elimination, dehydrohalogenation, addition and substitution. So this is a halide compound, or you can take simply as RX in general, and this is converted into ROH. How this could be done? X could be substituted by OH group. Therefore, you can use any nucleophile here to substitute this X minus. So therefore it could be only a substitution reaction. OH is substituting this halogen from this compound to form ROH. Therefore option D is the correct answer. See, in 1997 such a simple question is asked, but nowadays we may not get such easy question. Okay, let's pray, no, we also will get such easy question in the upcoming years. The following reaction is described as, so here it's a secondary halogen compound. So Br is bonded to a carbon which is having only one hydrogen. So therefore it is secondary halide, and OH minus is a nucleophile. This is attacking and replacing this Br group, but it is attacking from the product. We can understand it is attacking from the back side, the back end of the carbon. That is why this OH comes opposite to this bromine, and all the other groups which are bonded to carbon, that is CH3, CH2 5 times. So they are all inverted from this side. So when OH minus is attacking this side, so in the intermediate, what will happen? At intermediate stage, a transition state will happen. That is, this will be partially bonded to carbon, and slowly this bond will be partially broken. Therefore, both OH and Br will be partially bonded to this carbon, and slowly the bromine bond gets weakened and Br minus will go away. At the same time, the inversion of these groups will take place. So the CH3 will be shifting to this side, and hydrogen will be shifting to this side, and CH3 will be shifting to the other side. See here, complete inversion has taken place. Let's see where this is. That is why it is SN2 reaction. This is SN2 reaction. So it happens in a single step. The nucleophile is attacking the carbon from the back end, and inversion of the product structure takes place. Therefore, it could be only SN2 types of reaction. Hope you have understood it clearly. Therefore, option A is the correct answer. Reactions of tertiary butyl bromide with sodium methoxide produces. So they are given 4 options. Let us take the substrate first. Tertiary butyl bromide, CH3, Br, CH3, CH3. Okay, this is tertiary butyl, this is bromide. It is treated with sodium methoxide. So methoxide is CH3O and sodium. So this is Na plus and CH3O minus. So in this salt, this CH3O minus is a strong base. It is a strong base. So in the presence of strong base, elimination reaction will take place. Alpha beta elimination reaction will take place. Therefore, bromine from this alpha carbon and hydrogen from all of them are beta carbon. All of them are beta carbons. Therefore, one of the hydrogens from any one of the beta carbons will combine with this Br, and HBr will be eliminated. Therefore, minus HBr. Therefore, what will you get? CH3, C, double bond, CH2, because this hydrogen and Br is eliminated and this CH3 remains. So this is isobutylene. What is this? Isobutylene. So is there any product by name isobutylene here? Yes, option D is isobutylene. Therefore, this could be the correct answer. Hope you understood this. See, suppose tertiary butyl bromide undergoes hydrolysis with methanol instead of CH3ONA. If it is with CH3OH, then substitution reaction might take place. But here with sodium ethoxide, so that the sodium methoxide, the methoxide is a strong base. Therefore, here elimination reaction takes place. Remember this point. With strong base, elimination reaction will take place. So that's very important. So this point will help you to solve many such problems for you. So here they are given sodium methoxide. In some other problem they will give you sodium ethoxide or potassium methoxide. So everything is same. So that alkoxide will be the strong base. Therefore, elimination reaction will take place. So that's a point you need to remember here. Hope you understood it clearly. Grignard reagent is prepared by the reaction between, okay, instead of seeing all those things, if you know the answer, you know it is prepared from any alkyl halide with magnesium in the presence of dry ether. So now we can check the answer which is correct. Magnesium plus alkane, no. Magnesium plus aromatic hydrocarbon, no. Zinc plus alkyl halide, no. Magnesium plus alkyl halide, yes. So this is alkyl halide and magnesium. So this is distilled in the presence of dry ether. We will get Grignard reagent. When alkyl halide is distilled with magnesium in the presence of dry ether, Grignard reagent is prepared. That is alkyl magnesium halide. Why we have to use dry ether? So if it is moist, what will happen? So if there is moisture, that is nothing but water. So Grignard reagent reacts with water to give what? Alkane. To give alkane. So that is why the ether what we are using should be dry. It cannot have any moisture. So this question also may be asked as a separate question. Why we need to use dry ether? So if it is moist ether, that water will react with Grignard reagent to produce alkane. So in order to avoid that, dry ether is used. So here the option is option D, magnesium plus alkyl halide. Of course, in the presence of dry ether, that should have been mentioned here. Hope you have understood it clearly. Chlorobenzene reacts with magnesium in dry ether to give a compound A, which further reacts with ethanol to yield the given the products. See, first chlorobenzene it reacts with magnesium in the presence of dry ether. So just now we had seen in the previous question, Grignard reagent will form. Okay, this gives a compound. This is compound A, which further reacts with ethanol to yield what? So let us consider this as compound B. So they are asking what is compound B. So we will work it out here. So here when magnesium reacts with chlorobenzene in the presence of dry ether, what will we get? We will get phenyl magnesium chloride. Phenyl magnesium chloride. This is a Grignard reagent. And when this is treated with ethanol, so what will you get? So that is the second step. We take it here. Okay, this is Grignard reagent. So Mg, here Mg bond, Cl, Grignard reagent, phenyl magnesium chloride. It is treated with ethanol, C2H5OH. So in Grignard reagent, this phenyl group, this R group is carbon ion, that is R minus. So this is a negative ion. So Mg is partially positive here and Cl minus. Because Mg is more electropositive than this carbon, therefore the electron will go towards the carbon because carbon is having more electronegativity. Okay, therefore Mg will be partially positive, this carbon ion will be partially negative here. So therefore here in ethanol C2H5OH, H is plus and C2H5O is minus. Therefore this H plus will be bonded with this R and forms benzene. This R is phenyl here, therefore this is, now it becomes benzene because that hydrogen is bonded here. And now the bond is broken, that Mg will be bonded with what? The Cl is positive. What is negative here? O, C2H5 is negative. Therefore that is combining with this positive magnesium here. Okay, therefore what is formed? Benzene is formed. So you need to remember here this phenyl group in Grignard reagent RMgX. This R is a carbanion. It is not R plus like in alkyl halide compound. It is a negative ion, carbanion. Therefore, anything positive only will combine with this R. Therefore, here from ethanol that H plus positive combines here. Thereby benzene is formed. Therefore, which answer is correct here? Answer B is correct. Hope you have understood it clearly. Benzene reacts with N-propyl chloride in the presence of anhydrous aluminium chloride to give. So they are given 4 options here. Now let us take benzene. Plus N-propyl chloride. So what is N-propyl chloride? CH3, CH2. CH2 is N-propyl. That is normal propyl chloride in the presence of anhydrous aluminium chloride. So that is dry aluminium chloride. So what will happen here? So this chlorine will be absorbed by this anhydrous aluminium chloride and forms AlCl4 minus. So leaving behind what? CH3, CH2, single bond, CH2, carbocation. So now this carbocation, this is acting as an electrophile. So that will be bonded to the nucleophile benzene, because benzene is enriched with these pi electrons. Therefore, this this propyl carbocation will be bonded to this benzene. But here, if you take this one, so this is primary carbocation. This is primary carbocation, but this carbon is having positive charge. The neighboring carbon, that is the alpha carbon, having 2 hydrogens. Therefore, what can happen? Hyperconjugation will take place. So this is positive. Therefore, this electrons will move towards this positive one here, and hydrogen will be shifted here. So thereby it becomes what? CH3, CH, and this becomes CH3, and this carbon becomes positive. Now this is a secondary carbon, secondary carbocation, because this carbon is having only 1 hydrogen. So secondary carbocation is more stable than primary carbocation. That is why this change, this shift takes place. Now this electrophile will be bonded with benzene. So how? So this is benzene. So this will undergo substitution reaction. One of the hydrogen will be substituted by this isopropyl group. Therefore, isopropyl benzene you will get, and the hydrogen substituted here, that will combine with this AlCl4 minus to form what? HCl, and it will give back that catalyst aluminium chloride, anhydrous aluminium chloride will come out as it is. So therefore, what is the main product formed here? Isopropyl benzene. So initially you will get primary carbocation, but due to the presence of hydrogen in the alpha carbon, hyperconjugation takes place, thereby secondary carbocation is formed. Secondary carbocation is more stable than the primary carbocation. Now this acts as an electrophile, combines with benzene to form what? Isopropyl benzene. So here this CH3, CH, this isopropyl carbocation. Now this will be attacking the benzene here and creates a bond, and this hydrogen will be substituted, and that hydrogen only will combine with this aluminium AlCl4 minus ion, it combines with this, forms HCl and gives back the original aluminium chloride. Hope you have understood it very clearly. Therefore here the correct option is what? Option D, isopropyl benzene is the correct option. Which chloro derivative of benzene among the following would undergo hydrolysis most rapidly? With aqueous sodium hydroxide to furnish the corresponding hydroxyl derivatives. See, all the 4 compounds are chlorobenzene. See here it's all chlorobenzene. Okay, but which derivative will undergo hydrolysis most rapidly? See, if you take compound D, it is only chlorobenzene. So in chlorobenzene already we have learned many times in previous questions. So this bond becomes stronger. This becomes shorter and stronger due to the resonance, because chlorine is having 3 lone pair of electrons. So that is in resonance with the 3 pi bonds in benzene ring. Therefore this bond becomes stronger and shorter. Therefore this will not undergo hydrolysis rapidly. And in this case, this NMe2, that is dimethylamine. So this is electron donating group. So this will donate the electron to benzene ring. Therefore, it deactivates this chlorine. Therefore, this also will not be hydrolyzed so easily. But if you take option B, here there is a nitro group, NO2 group. Nitro group is electron withdrawing group. Electron withdrawing group. Therefore, it withdraws electron from benzene and making this chlorine more active. Therefore, it can easily undergo hydrolysis. Therefore, this could be one of the answers. But if you take option A, there are 3 nitro groups, 2 in the ortho position and 1 in the para position. All of them are electron withdrawing group. So it makes the chlorine more active. Therefore, this can be removed or replaced or substituted very easily than the option B. Therefore, option A is the correct one. So the electron withdrawing group that is pulling the electron towards NO2 group. So thereby it is activating the chlorine. So therefore it can easily leave the benzene ring. Therefore this will undergo hydrolysis most rapidly. Hope you understood very clearly. Which of the following is an optically active compound? So we know the compound having a chiral carbon, that is, it is bonded to 4 different groups, then it is a chiral carbon, then it is optically active. So now let us see here one by one. First one is 1-butanol. What is 1-butanol? So 1, 2, 3, 4 carbons and alcohol in the first carbon. So N, therefore everything is single bond, therefore CH3, CH2, CH2, CH2. See, all the carbons are having more than one hydrogen. So that means 2 similar groups in every carbon. Therefore it does not have a chiral carbon, therefore it is not optically active. Second one, 1-propanol. So prop 3 carbon, then 1 OH. Since N all single bond, therefore you can put CH3, CH2, CH2. Here also all the carbons are having more than one hydrogen. Therefore 2 groups are similar, minimum 2 groups are similar. Therefore this also cannot be optically active because it does not have any chiral carbon. Therefore option B is ruled out. What is option C? 2-chlorobutane. So butane 1, 2, 3, 4. N, therefore all single bonds. 2-chloro, so in the second carbon there is chlorine. Now you fill up everything with hydrogen, H3, and here 3 bonds, therefore 1 hydrogen. Here 2 bonds, therefore 2 hydrogen, 3 hydrogen. Okay, now you take this carbon, 3 hydrogen, 2 hydrogen, 3 hydrogen. So it cannot be optically active. Here only 1 hydrogen, that you write it here, bond hydrogen. Now you check this carbon, one bond is connected to hydrogen, the other bond is connected to methyl, the other bond is bonded to chlorine, the other one is bonded to ethyl group. All the 4 groups are different. Therefore this carbon is a chiral carbon. Therefore it can exhibit optical isomerism. Therefore this compound is optically active. Therefore option C is correct. Then what about option D? We need not go for option D because we got already the correct one. But let us check whether it is having chiral carbon or not. 4-hydroxyheptane. Hept means how many? 7. 1, 2, 3, 4, 5, 6, 7. 4-hydroxy. 1, 2, 3, 4. So in the 4th carbon, hydroxy. So it's ending with N. Therefore all bonds are single bonds. Okay, now you fill it up with hydrogen, CH3, CH2, CH2, here CH, here CH2, CH2, CH3. So this hydrogen, we can write it here. Now all these carbons cannot be chiral because it is having minimum 2 hydrogen in them. Therefore it cannot be a chiral. What about this one? So this one is bonded to hydrogen, the other one is bonded to OH. This is bonded to propyl group this side also propyl. These 2 groups are same. Therefore it cannot be chiral. Therefore this also cannot be optically active. Therefore only compound C is the correct one. Hope you have understood it very clearly. Trichloroacetaldehyde reacts with chlorobenzene in the presence of concentrated sulfuric acid and produces, so trichloroacetaldehyde, CCl3 CHO. This is trichloroacetaldehyde or chloral, reacts with chlorobenzene in the presence of sulfuric acid. See, in the presence of sulfuric acid, H2SO4. So sulfuric acid has great affinity for water, therefore that will absorb water from these 2 reactants. So what is the other one? Chlorobenzene. So how we can write chlorobenzene? So we can write, so this is 1-chlorobenzene, this is another chlorobenzene. So this is chlorobenzene. Chlorine is bonded to benzene here. Therefore, ortho, meta, para. So from the para position, the hydrogens, the two hydrogen from two phenyl group from the para position combined with this oxygen in chlorol, and this water molecule is eliminated. So what for this? In fact, it is concentrated sulfuric acid. Concentrated sulfuric acid has great affinity for water. So it absorbs this water molecule. And now this CH will be bonded directly to this phenyl ring, and another one will be bonded to this phenyl ring. So this is what is a product we have to check which is a product formed here. So what is a product will form here? So CCl3, CH, then what else? So this is bonded to one benzene ring, that is phenyl group, and in the para position there is chlorine, and this is bonded another, and this is a product formed plus water. So where this product is available now, whether it is in option A, B, C or D. So CCl3, so nowhere in product A there is nowhere CCl3. In option B also there is no CCl3. In option D also there is no CCl3. Therefore A cannot be correct, B cannot be correct, and D also cannot be correct. But in option C there is CCl3, yes. Then CCl3 is bonded to CH, yes, it is bonded to CH, and one bond is bonded to benzene ring in para position chloro. Therefore it is bonded to this benzene in the para position chloro. The other bond is also bonded to another benzene. See, it is another one bonded to benzene ring and chloro. Therefore option C is the correct one. So what is this compound? This is a compound called DDT. So dichloro, diphenyl, so two chlorines are there, therefore dichloro. So they are present in the para position, therefore it may be known as para dash dichloro, para dash dichloro. Then two benzene rings are there, therefore diphenyl. What is the three chlorines are there, therefore trichloro, and here one carbon and two carbon, that is bonded by single bond, therefore ethane. So para dash dichloro, diphenyl, trichloroethane. This is what is in short known as DDT. So this is used as an insecticide. So in agriculture, it is all used as insecticide, DDT, dichloro, diphenyl, trichloroethane. So they might ask you how it is prepared also. So if you have learned this DDT, how is it prepared? You could have easily answered this question. Hope you have understood it clearly. Industrial preparation of chloroform employs acetone and phosgene, calcium hypochlorite, chlorine gas, sodium chloride. So this calcium hypochlorite is otherwise known as what? CaOCl2, bleaching powder. So this is nothing but bleaching powder. So you should know this. Sometimes they will ask you, they might give you bleaching powder also instead of giving calcium hypochlorite. The formula is CaOCl2. See, acetone reacts with calcium hypochlorite to produce chloroform. So how that is done? You should have learned the preparation of chloroform from acetone. So how this can be prepared? CaOCl2 is a bleaching powder, reacts with water initially. You will get calcium hydroxide plus chlorine gas. So this chlorine gas acts as chlorinating agent, and it chlorinates that acetone. So initially we are adding acetone. See, acetone plus chlorine. So three hydrogens will be substituted by this chlorine. Therefore you will get CCl3, COCH3. That is trichloroacetane will form. Now this trichloroacetane will react with this calcium hydroxide to give chloroform. See, what is calcium hydroxide? CaOH twice. See, for our convenience sake I am writing this. And what is trichloroacetone? CCl3, COCH3. CCl3, COCH3. So now this hydrogen will combine with this Cl3, will form chloroform, and this will form another chloroform, CHCl3. Therefore two chloroform will form, 2CHCl3. So chloroform. So what is the other product you will get? Ca, here there is O, and after that what is there? CO and CH3. Similarly, OCOCH3. So this is nothing but what? Calcium acetate. Calcium acetate. This is the byproduct. So what is the main product? Our chloroform is the main product. Therefore, if you have learned the preparation of chloroform by treating acetone with calcium hypochlorite, that is bleaching powder, moist bleaching powder. So only then you will get water here, only then chlorine gas will be liberated, then the further reaction will take place. So if it is dry, it cannot be done. So only in water this reaction could be carried out. Okay, instead of acetone, sometimes ethanol also can be used. Ethanol also can be used. So that also might be asked. Instead of acetone, if they give ethanol, you should not blink. So both of them can be used, but in both cases, what is the reagent? Calcium hypochlorite. What is its formula? CaOCl2. Its other name is bleaching powder. Okay, hope you understood it very clearly. Therefore, the correct answer here is calcium hypochlorite, option B. Please. See, phosgene is a common name for phosphoryl chloride, thionyl chloride, carbon dioxide and phosphine, and carbonyl chloride. So here our memory is tested. So phosgene is otherwise known as carbonyl chloride, or the commercial name for carbonyl chloride is phosgene. So what is the formula for carbonyl chloride? COCl2. So this is a poisonous gas. This is a poisonous gas. And what is the formula for carbon dioxide and phosphine? Carbon dioxide, CO2, phosphine is PH3. What is thionyl chloride? SOCl2. That's it. And then what is phosphoryl chloride? POCl3. See here, nothing to understand, nothing to derive. So our memory is tested. So phosgene's chemical name is carbonyl chloride. Its formula is COCl2. Hope you have understood it clearly. Hope you liked the entire video lesson. Please click thumbs up, comment, share and subscribe without fail. Thank you very much for watching this video. Until we meet next time. Bye bye.